The surface rolls gently under a wide grey sky, the kind of ocean that looks empty until something massive breaches the silence beneath it. There is little to see from above. No reefs, no shoals, only open water stretching unbroken toward the horizon. But in the deep below, sound moves through this world with extraordinary reach. It carries across basins and ridges, past underwater mountains and along vast plains of sediment. In this immense acoustic chamber lives an animal whose primary sense is not sight or smell or even touch, but vibration on a planetary scale. The blue whale navigates the world through sound waves so powerful and so long that they bend around continents and travel distances no land creature could comprehend. For this giant, the sea is not silent. It is alive with low-frequency pulses that reveal location, season, weather, and the presence of life across extraordinary distances. Blue whales inhabit a sensory world defined not by what they see, but by what they hear. Vision plays only a minor role in their daily existence. In open water, light fades rapidly, and even in daylight, the visibility of shapes and colors becomes unreliable. The blue whale's eyes are small relative to its body, offering only modest clarity in the near field. But this is of little consequence, because blue whales rely on a sensory system far more suited to the scale of the open ocean. A set of inner ear structures and skull-conducting bones adapted to detect vibrations of incredible length and depth. These sounds occupy frequencies so low that humans cannot hear them at all, and yet these frequencies propagate through seawater with remarkable efficiency. A blue whale call can measure longer in wavelength than the whale itself, spanning tens of meters in a single undulation. When the animal releases one of these vocalizations, the sound does not simply drift away. It pushes through water in long, stable waves that resist decay. These waves travel across enormous distances, hundreds of kilometers, sometimes exceeding 1,000, weaving through underwater canyons and bouncing off the slopes of seamounts. In some documented instances, blue whales in distant ocean basins have responded to calls emitted far beyond any range humans would consider possible. Their world is threaded with a slow, deep hum that carries the acoustic fingerprints of storms, shifting currents, migrating pods, and geological features scattered across the planet. This ability stems from the blue whale's specialized auditory anatomy. At first glance, the skull seems like a fortress built for size rather than sensitivity. But inside this massive framework lies a delicate system of bones, adapted to transmit sound through vibration rather than air conduction. Because underwater hearing is not as simple as receiving sound through open ear canals, blue whales evolved thick, dense bones called tympanic bullae, paired structures that house the middle and inner ears. These bullae are acoustically isolated from the skull by ligaments, allowing sound to vibrate them independently. When low-frequency waves roll through the whale's environment, they cause the entire skull to resonate subtly. These vibrations transfer through the bullae into the cochlea, where sensory hair cells detect the minute changes in pressure. The scale of these vibrations is staggeringly low. A blue whale's cochlea is long and tightly coiled, optimized to detect frequencies that fall below 20 Hz, frequencies that travel vast distances underwater. To human senses, these vibrations would feel less like sound and more like distant tremors. Imagine the deepest thunder felt rather than heard. This is the language of blue whales. It is slow, resonant, and spacious. Their communication occurs not in short chirps or sharp pulses, but in drawn-out moans and rhythmic patterns that can persist for dozens of seconds. A single call may ripple outward for hours as it travels through the deep, bouncing off layers of temperature and salinity that guide its movement like channels carved through the sea. What does a blue whale hear when it listens to its world? Not silence. The ocean is filled with sound produced by wind, currents, rain, cracking ice, volcanic activity, and the movements of other marine life. But among these noises exist acoustic structures that reveal geography and events occurring far beyond the whale's immediate surroundings. When deep storms churn the ocean thousands of kilometers away, The pressure changes and turbulent energy from these events produce low-frequency noise that travels far. The whale may sense these storms as a faint rumble echoing through the deep, providing clues about changing weather or shifting ocean conditions. Even underwater mountains, seamounts, contribute to the whale's acoustic map. When waves crash above the peaks of these submerged giants, or when currents push water upward along their slopes, the turbulence generates deep, low-frequency vibrations that radiate outward. A blue whale may pass above a seamount and recognize it through these vibrations alone, without seeing its shadow or sensing its silhouette. These features become landmarks in a world without fixed visual reference points. Most remarkably, blue whales hear one another across these distances, maintaining acoustic contact over expanses that would render sight and smell useless. A whale feeding near Antarctica may communicate with another far along a migration corridor. Their calls overlap, intersect, and harmonize into a kind of long-distance dialogue, allowing individuals to coordinate loosely across regions. The ocean becomes not an empty expanse, but a vast resonant network connecting whales through sound. Hearing dictates nearly every aspect of a blue whale's life. During migration, whales follow acoustic gradients, moving toward areas where the density of krill increases or where other whales have gathered. Krill themselves create subtle sounds when moving in massive swarms, but these signals are not strong enough for navigation. Instead, blue whales use the calls of other whales as indicators of feeding success. Where whales are calling more frequently, food is plentiful. Where calls diminish, conditions are poorer. In this way, the species maintains cohesion without grouping tightly, preserving access to vast feeding grounds without overcrowding any particular zone. The process of listening and mapping requires robust conduction of sound through the whale's body. The skull absorbs vibrations across its broad surface, and these waves transfer through internal bone structures with incredible efficiency. Sound, unlike light, does not scatter in the deep. Instead, it glides through the water column along channels created by differences in temperature and pressure. These channels allow long-distance communication across entire oceanic regions. Blue whales exploit these pathways instinctively, aligning their calls with conditions that favor propagation. Their deep moans are structured not only by anatomical capability, but by environmental opportunity. In these low frequencies, the ocean becomes a planet-sized instrument. The whale does not hear merely in front of it or behind it, it hears globally. Its sensory world is shaped by distances that span regions rather than meters. The deep, slow pulse of the ocean floor, the whisper of distant storms, the quiet shift of migrating pods, all reach the whale in forms that may feel abstract to human perception, but carry precise meaning to the whale. These vibrations provide a sense of orientation more reliable than vision, in a world where distances stretch beyond the horizon and light fades rapidly. The remarkable part of this adaptation is its evolutionary efficiency. A huge animal does not require high visual acuity to find food, avoid threats, or navigate. Instead, it requires a sensory system that matches its scale and its environment. The blue whale evolved to hear like a mountain listens to the wind, not through sharpness or speed, but through depth and resonance. This is how it perceives its surroundings, as a collection of infrasonic waves that describe the sea not in detail, but in structure. Even social communication depends on this. During breeding season, males produce complex songs, sometimes lasting hours or repeating endlessly across days. These songs are not melodically complex in a human sense, but they carry information about identity, location, and physical condition. Other whales hear these patterns from extraordinary distances, integrating the signals into their understanding of the habitat and its occupants. Females may navigate towards certain calls. Males may adjust their own patterns in response. This acoustic behavior shapes the social landscape of whales across entire ocean basins. When a blue whale swims through deep water, its body resonates subtly with the world around it. It is not simply moving through the sea, it is listening to it constantly. Its skull, its ribs, even the tissues along its sides transmit vibrations that come from every direction. The whale constructs a mental map of the world, not from colors or shapes, but from the shifting harmonics of the sea. What is near produces sharper changes. What is distant produces long, droning textures. Together they form the sensory backdrop of the whale's existence. In the quiet, expansive water where their giants roam, the blue whales inhabit a dimension where sound defines reality. For them, the ocean is not a place of visual beauty or bright detail. It is a resonant chamber where every distant event becomes a vibration in the body, where communication spans hundreds of kilometers, and where navigation depends on listening to the deep, patient heartbeat of the planet itself. The deep ocean is a world without light. Sunlight dies quickly as it passes downward, thinning to a pale haze by a few hundred meters, before vanishing entirely into a blackness so complete that even the closest objects become invisible. Here, beneath the weight of thousands of meters of water, the sea is ruled by silence and shadow. The pressure is immense, the cold relentless, and the only certainty is darkness. In this realm, eyesight is useless. Color disappears. Shapes dissolve. Boundaries blur until the world becomes one unbroken void. For most mammals, this would be an impossible environment. For the sperm whale, it is home. The sperm whale occupies the deep in a way no other predator can, plunging downward on long, slow descents that may last more than an hour. As it sinks, its heart rate drops, blood shifts into specialized reservoirs, and its lungs collapse safely to reduce nitrogen absorption. But even as these physiological changes unfold, its primary sensory system remains alert. Unlike the blue whale, which listens to low-frequency messages that travel across ocean basins, the sperm whale perceives its world in laser-like packets of high-frequency sound, pulses so powerful that each one becomes a snapshot of the dark landscape ahead. At the front of the sperm whale's head lies one of the most remarkable biological structures in the animal kingdom, the spermaceti organ. It fills much of the head, giving the whale its characteristic block-like shape. But this organ is far more than a mass of waxy oil. It functions as a sophisticated acoustic lens. When the whale produces a click, the sound originates in a small pair of nasal sacs, sometimes called the monkey lips, which snap together rapidly, generating a sharp pressure wave. This sound then travels through the spermaceti organ and the dense tissue surrounding it, becoming focused and directed like a beam of energy. The spermaceti organ acts as the core of the system, controlling the direction and strength of the sound beam by adjusting its density and internal geometry. Each click is not merely a sound, it is a pulse of energy so intense that it can stun small prey at close range. These clicks produce some of the most powerful biological sounds in the ocean. They travel outward through the water in tight, concentrated packets. When they strike a squid or a fish, they bounce back in altered form. These returning echoes carry information about distance, shape, texture, movement, and even density. To a sperm whale, every click becomes a question thrown into the void, and every echo becomes an answer. As the whale moves deeper, descending into zones where pressure squeezes the water and temperature drops sharply, its clicks begin to reveal the world around it. Even in total darkness, the whale's echolocation describes everything in remarkable detail. Long before it sees a squid, if seeing is even the right word, it understands the creature's movements through the echoes returning from its tentacles. A squid's body reflects sound differently than its fins or arms. A tight school of fish produces a shimmer of echoes, each tiny body sending back a distinct vibration. Even the seafloor echoes with deeper, heavier responses, allowing the whale to contour the landscape as it moves through it. To humans, this sensory perception would feel alien. But for the sperm whale, it forms a three-dimensional image that is just as rich as sight. Each click travels outward at high speed, bouncing off objects and returning at different intervals. The whale's brain processes these echoes with extraordinary efficiency. The lower jaw plays a central role in this interpretation. Inside the jaw lies a channel filled with fat-rich tissues that are acoustically transparent, allowing sound waves to travel through them with minimal loss. These tissues funnel the returning echoes toward the ears, which are set deep within the skull and suspended in dense bone to isolate them from interference. This anatomical arrangement gives the sperm whale a directional sense of hearing that rivals precision instruments. It can determine whether a squid is above or below, whether it is rotating, fleeing, or hovering. It can detect slight differences in distance measured in fractions of a meter. It can perceive density differences in the water column that reveal the presence of organisms too small to reflect strong echoes. The result is a kind of acoustic vision, a picture built entirely from returning sound. The deeper the whale goes, the more essential this becomes. At depths where bioluminescence flickers briefly across drifting particles, the whale relies almost entirely on echolocation. These environments host some of the most elusive prey in the ocean, large squid that swim with silent pulses of their mantle, avoiding predators through agility rather than strength. To the squid, the deep is a refuge from surface hunters. To the sperm whale, it is a hunting arena filled with three-dimensional silhouettes carved from sound. As the whale approaches its prey, the click pattern shifts. Slow, powerful clicks become more frequent, then rapid, then faster still. This acceleration, sometimes called a buzz, signals the moment when the whale has locked onto a target. The rapid-fire pulses provide a torrent of information, allowing the whale to track any sudden movement. Squid are capable of fast bursts of speed, expelling jets of water to pivot quickly. But even this motion creates acoustic signatures the whale can interpret. The animal is able to predict movement through echo patterns alone. When the whale closes in for the final strike, there is no need for sight. It opens its jaw and uses suction to draw the squid inward. The tentacles may writhe or strike outward, but the whale's thick skin and powerful musculature absorb the impact. Its mouth closes and the descent continues, often uninterrupted. This efficiency is crucial. A single deep dive may require enormous energy. The whale must maximize prey capture with minimal deviation. While hunting is the most dramatic use of echolocation, the sperm whale uses this sense to navigate the deep as well. The ocean at extreme depths is not uniform. It contains cliffs, ridges, valleys, and fault lines. Sound waves reveal these features through returning echoes that differ in speed and pitch. A distant seamount produces a heavy, resonant echo that arrives after a noticeable delay. A vertical wall of rock produces a sharp, rapid return. These distinctions allow the whale to orient itself along the underwater terrain, maintaining migration routes that span thousands of kilometers. Communication also plays a role in this acoustic world. Sperm whales produce coders, sequences of clicks arranged in distinct patterns that serve as social signals. These coders carry information about identity, group membership, and behavioral intention. They are exchanged among whales in the dark depths where visual cues are irrelevant. The same high-frequency structures used for hunting become tools of culture and cohesion. Different groups have distinct coder patterns, almost like dialects, and these acoustic signatures help maintain social boundaries. The whale's perception of the deep is therefore not merely functional, it is also communal. It shares the darkness with others, and through coded sound constructs a social landscape layered on top of its sensory map of the environment. This dual role of echolocation, both for hunting and communication, gives the sperm whale one of the richest acoustic lives in the animal kingdom. In the pitch-black world beneath the thermocline, the sperm whale sees without light. Its vision is not shaped by colors or outlines, but by the timing, strength, and character of echoes returning from its own powerful clicks. This way of experiencing the world creates a sensory environment humans can barely imagine. It is a world built from vibration and response, from questions sent into the abyss and answers carried back from creatures drifting in the dark. The sperm whale swims through this world with certainty. Every click is a new pulse of illumination. Every echo adds detail to the unseen. Every dive unfolds as a journey through a realm sculpted not by sunlight, but by sound shaped through millions of years of evolution. In this acoustic dimension, the sperm whale is not blind. It is the master of a sonar domain so refined that even the vast pressure-blackened deep becomes a landscape of clarity. Its perception reaches where light cannot. Its world is built from echo. And in the quiet, cold layers of the planet's greatest depths, the whale's voice becomes the instrument through which the sea reveals itself. The surface looks calm, a sheet of muted silver broken only by the slow push of the swell, but beneath it the water feels charged. Cold currents slide along the continental shelf like invisible highways, and through this shifting world moves an animal tuned to signals so faint they border on the impossible. The great white shark does not search blindly. It does not patrol with the uncertainty of a creature hoping to stumble upon prey. Its world is stitched together by trails of information that humans cannot sense, woven from molecules, electrical pulses, and minute disturbances in the water. What appears to us as a vast empty blue is for the great white a layered map, rich with sensory landmarks that lead it from patience to precision, from stillness to strike. In this chapter, the shark does not rise as a mindless killer, but as a master of sensory integration, reading the ocean with an intelligence shaped by millions of years of evolution. Far offshore, the story begins with something almost absurdly small, a single droplet of blood released into the cold Pacific. It dilutes instantly, becoming a whisper of organic molecules caught in the turbulence of waves and currents. Yet within this haze rests a signature that carries meaning. Great whites possess an olfactory system so sensitive that they can detect concentrations measured in parts per 10 billion. To them, scent does not arrive as a vague presence, but as a structured pattern. The shark interprets gradients of smell the way a seasoned tracker reads fresh footprints in the soil. Even in an ocean where currents twist and collide, it can determine the direction from which the trace grows stronger, following the thickening thread back toward its origin. This first cue is not a target, nor even a promise of one. It is the opening of the hunt, the moment when the shark's swimmers shift from cruising beats to a more intentional rhythm. As it approaches the general area, another layer of sensory input rises from the background. The great white shark carries around its head and snout a constellation of tiny gel-filled pores called the ampullae of Lorenzini. To the eye, they are merely dark dots scattered like freckles across the skin, but their function is extraordinary. Each ampulla connects to a sensory cell capable of detecting minute electrical changes in the water. Living muscle produces electrical signals when it contracts. A heartbeat is an electrical rhythm. A seal flexing its flippers sends out pulses of bioelectricity that radiate through the water like the faint hum of distant machinery. The shark senses these signals at amplitudes of less than a billionth of a volt, a level of sensitivity nearly unmatched in the animal world. What begins as a chemical trail transitions into an electrical landscape. The shark shifts from one map to another as it closes in. Scientists once believed that sharks relied mostly on smell, placing vision second and electroreception a distant third. Modern research suggests the opposite hierarchy when the shark enters attack range. Smell provides the invitation to the hunt, vision provides confirmation, and electroreception delivers the final, precise coordinates. As the shark glides through the water, small alterations in the pattern of electrical noise around it reveal the proximity and orientation of another animal, even one hiding in a cloud of silt or swimming behind a rock. The great white does not need a clear view. It needs only the electric shadow produced by a beating heart. Close to the surface, a young fur seal veers in rapid evasive arcs, unaware that its movement creates a dynamic electrical trace. Every flick of its muscles, every rapid twist, creates a cascade of electrical currents picked up by the shark's ampullae. Seals evolved remarkable agility as a countermeasure against predators, performing unpredictable turns and sudden bursts of speed. Yet every twitch of those powerful muscles lights up the shark's sensory map like a flare. The shark does not track the seal's silhouette. It tracks the spatial distribution of electric fields, reading motion without relying on visibility. As the shark closes the last stretch, vision begins to matter, though not in the way humans expect. Great whites have excellent vision, capable of detail and contrast in dim light, but in the chaotic interface of breaking waves, eyesight becomes unreliable. Light bends and fractures, reflections distort shapes, and surfaces flash with confusing glare. This is why the great white approaches from below, using the vertical plane where light silhouettes the prey cleanly. The seal appears above as a single dark form framed against a bright surface, providing a sharp contrast. But even now the shark does not commit until its electrical map is complete. The moment of decision is not theatrical. It is biological. The shark's brain integrates sensory input, blending smell, vision, and bioelectric data into a single decision: attack. Its tail delivers a sudden burst of power, transforming smooth cruising into a torpedo-like ascent. Water compresses around its snout. Muscles along its flanks contract with massive force. And then comes the final adaptation, perhaps the most misunderstood of all. The shark closes its eyes. Humans often interpret this as fear of being injured by struggling prey, and partly that is true. The great white's eyes roll back, exposing a protective white membrane designed to shield the delicate retina from claws or flippers. But there is a deeper evolutionary logic. In the last meter before impact, vision becomes useless. The shark is moving too fast, water turbulence becomes too violent, and the surface glare overwhelms any remaining clarity. In those final milliseconds, the shark switches fully to electrical and mechanosensory guidance. The ampullae track the prey's electric outline. The lateral line system detects changes in water pressure created by the seal's movement. The entire attack sequence rides on these invisible fields. In the dark sensory world beneath the surface, the seal is not a shape. It is an electric rhythm. It is a cluster of voltage gradients. It is a pressure disturbance in the fluid. The shark bites not at the animal's visible body, but at the center of this electrical signature, striking the precise spot where muscle activity and heartbeat are concentrated. This is why great white attacks appear uncannily accurate. Even when striking from below without seeing the final moment, the shark lands its bite on the torso where vital organs are located. It is not guessing. It is following a map humans cannot perceive. After the strike, the water explodes into turbulence. The seal twists violently, and the shark often releases it, creating a behavioral pattern known as the bite and wait strategy. This is not clumsiness. It is energy economics. Great whites are warm-bodied compared to many fish, maintaining elevated internal temperatures that allow powerful bursts of acceleration. But these accelerations cost significant energy. A wounded seal can only flee for a short period before weakening. The shark uses its electroreception to track the struggling animal again, homing in on the faltering electrical signals of organs under stress. As the heartbeat weakens, the shark's electrical map grows easier to read, the prey's movements becoming slower and more chaotic. The shark re-engages efficiently when resistance is minimized, conserving energy. Even beyond hunting, electroreception shapes the shark's understanding of the ocean. Some researchers believe great whites may use the Earth's magnetic field to aid long-distance navigation, detecting the weak electromagnetic gradients generated as seawater moves through the planet's magnetic field. This could explain their ability to travel thousands of kilometers across featureless open water and still return to the same hunting grounds year after year. The ampullae, originally evolved to detect prey, might also allow the shark to perceive the planet's magnetic landscape like a vast underwater compass. To the great white shark, the ocean is not empty, it is not murky, it is not confusing. It is illuminated by fields and signals humans cannot imagine. Smell forms broad chemical pathways that stretch across kilometers. Vision offers silhouettes and contrast. Pressure waves reveal movement. But electroreception turns the ocean into a living circuit board, filled with glowing outlines of every animal that moves, breathes, or flexes beneath the surface. In this world, the shark is not a brute force attacker. It is the quiet master of an electric map, reading life itself in currents measured not in meters or seconds, but in volts so faint they blur the boundary between biology and physics. The predator rises through the water once more, the sensory world around it alive with information. For the great white shark, hunting is not the chaos of pursuit. It is the art of interpretation, a methodical decoding of signals invisible to every other large predator in the sea. And in that silent, electrically lit world, it is unmatched. The midday water is blinding. Sunlight punches through the surface in sharp, fractured beams that scatter across drifting plankton and the backs of schooling fish. Every movement turns into a burst of glare. Every scale becomes a mirrored flash. Many predators avoid these hours, sinking deeper where the light softens and the world becomes easier to interpret. But one hunter thrives in this visual chaos. The barracuda rules the bright shallows, an animal built not for stealth through darkness, but for absolute precision in blinding daylight. Its long, torpedo-like body hangs motionless near the drop-off, suspended in the startling clarity of tropical seas, where the sun paints everything with hard edges and dancing highlights. It is here, in this punishing glare-filled world, that the barracuda's unique sensory design becomes unmatched. The barracuda's eyes sit forward on its head in a way that few fish can replicate. Most reef predators rely on lateral eye placement, giving them broad panoramic coverage but limited depth perception. The barracuda instead sacrifices that panoramic view for binocular overlap, the same principle that gives birds of prey the ability to judge distance with pinpoint accuracy. Its eyes face slightly inward, allowing visual fields to intersect and form a three-dimensional understanding of space. This adaptation offers the one gift needed for its hunting style: the ability to perfectly map a single straight line strike across several body lengths before the body even moves. All of this occurs in an environment where visibility is harsh, not gentle. Bright tropical waters create conditions that confuse most hunters. Scales reflect sunlight in rapid strobing patterns. Small fish swim in tight, shimmering formations that appear to blur into one flickering cloud. Glare from the rippling surface creates false shadows and sudden flashes that distort outlines. Many fish respond by relying more heavily on lateral line sensing or smell. Barracuda do the opposite. They lean fully into vision, but with a visual system specifically optimized for high-speed contrast detection. Their retinas contain a high density of cone cells, tuned to differentiate micro-variations in brightness and edge separation, even when the environment is filled with intense reflections. To a barracuda, the shimmer of prey is not a distraction, it is an outline. Where we see a chaotic dance of light, the barracuda sees patterns emerging from the noise. Its brain filters the glare through specialized neural circuits that enhance edge contrast. This means that even when a small fish creates a burst of reflective flashes, the barracuda can isolate the consistent shape underneath. The key for this predator lies not in color, but in the instantaneous shift from one shape to another. If a fish rotates, flickers, or hesitates for a fraction of a moment, that break in rhythm becomes the barracuda's anchor point, the moment when the prey's three-dimensional position is locked and calculated. Below the shimmering chaos, the barracuda holds its body almost unnaturally still. Its elongated frame does not sway with the current. Its fins do not flutter. This immobility is not laziness, it is strategy. Any unnecessary movement produces visible cues or pressure disturbances. By minimizing its signature, the barracuda becomes part of the water itself, a fixed point in a dynamic landscape. Only the eyes move, tracking subtle flickers through bands of brightness. When a small fish breaks away from a school or turns to feed on drifting particles, the barracuda immediately identifies it as a target. Prey selection is not random. The fish singled out is usually one whose rhythm appears slightly off, maybe a fraction slower, slightly out of formation, or positioned at a vulnerable angle. Once locked in, the barracuda begins its calculation. Unlike many predators that close distance gradually, the barracuda does not approach. It commits from where it hovers. The attack is based on the concept of straight-line intercept. The fish's brain projects the prey's movement vector, determining where it will be a moment later. Then aims not for its current position, but for the point where body and jaws will meet at maximum velocity. This requires significant depth perception, instantaneous processing, and trust in its own calculations. Even a small misjudgment of distance or angle could result in wasted energy or a missed strike. Evolution has rewarded the individuals that make these calculations flawlessly. When the strike begins, the transition from statue still to lightning fast is so abrupt, it borders on invisible. The barracuda's body remains rigid, but the tail executes one explosive flick, channeling tremendous power through the streamlined frame. Instead of bending its entire body into an S shape like many fish, the barracuda compresses the energy into a narrow range of motion that produces almost zero visual warning. A single contraction of the massive tail muscles launches the predator forward in a straight, unwavering trajectory. There is no second adjustment. The strike path is chosen before the movement starts, and everything afterward is momentum. Water resistance builds rapidly with speed. Many fish slow down during an attack as drag increases, but the barracuda's hydrodynamic shape minimizes this effect. Its long cylindrical form cuts forward cleanly, while scales arranged like overlapping plates reduce turbulence. Small, recessed fins prevent drag-producing vibrations. Everything about its anatomy is engineered for the one perfect burst of speed that defines its survival. As the barracuda approaches its target, vision drives the final adjustments. Unlike sharks, which may switch to electroreception or lateral line cues in the last instant, the barracuda keeps its eyes open and fixed. Its pupils adjust within fractions of a second to track brightness changes. Micro movements in the prey's body, a slight tilt of the head, a flick of a fin, a momentary shift in shadow, are processed in real time and compared against the original strike calculation. The barracuda's brain can modify the tail's second contraction within milliseconds, refining its straight-line trajectory without bending sideways or slowing down. This neural agility allows it to correct just enough to maintain accuracy while preserving most of its momentum. The final aspect of the strike reveals the predator's evolutionary specialty. The aim is not random. Barracudas target the head of the prey with astonishing consistency. This is the most efficient point of attack. A head strike prevents escape reflexes, disables locomotion instantaneously, and reduces the chance of messy wounds that disperse energy or attract competitors. The barracuda's jaws are lined with long, dagger-shaped teeth that interlock like scissors. These teeth do not merely puncture, they slice. When the barracuda bites down at full speed, the teeth create a clean incision that often decapitates small fish instantly or cripples larger ones with catastrophic precision. The killing moment itself is shockingly fast. A strike that began several meters away concludes in less than the time it takes sunlight to flicker across a single scale. The prey does not have the opportunity to twitch or change direction. This is because the barracuda's reaction time, the interval between seeing movement and initiating a muscular response, ranks among the fastest in the marine world. Its nervous system is built for immediate translation of sensory input into physical action, skipping intermediate processing steps that slower animals rely on. Where many predators must interpret signals, the barracuda's body responds almost reflexively. After the strike, the predator often slows abruptly, returning to stillness with the same discipline with which it launched. There is no wild thrashing, no chaotic pursuit. The kill has already been made cleanly. The barracuda grips the prey briefly, then repositions it headfirst to swallow it with minimal resistance. Once consumed, the barracuda does not display a burst of celebration or movement. It resumes its stationary hovering, ready to interpret the next flicker of contrast in the water. The remarkable efficiency of this predator lies not in brute force, but in sensory discipline. Its entire survival strategy centers on one theme: commit to a single perfect strike. It cannot afford repeated chases, nor extended pursuit. Its body is optimized for short-distance acceleration, not endurance. Its sensory system is built around rapid, high-fidelity visual processing, not low-light detection. This specialization is why the barracuda owns the sunlit water column, where glare blinds other hunters and reflections become confusing haze. The barracuda sees clarity, where others see chaos. In this world of bright water, harsh shadows, and shimmering confusion, the barracuda is a predator carved by evolution to excel where visibility is both abundant and deceiving. Its visual system isolates order from noise. Its body conceals energy in absolute stillness. Its strike unfolds along the shortest, cleanest path nature can produce. And in this environment, where seconds dictate survival, the barracuda's commitment to the straight-line kill makes it one of the most precise hunters in the ocean. The continental shelf fades into the deeper plane where sunlight collapses into muted blue, then into something closer to dusk. Here the water grows colder and heavier, pressing down on a seafloor paved with fine sediment that drifts like smoke at the slightest disturbance. This is not the world of swift hunters or bright flashes of color. It is a quiet, muffled domain where vision is unreliable and sound travels through a dense medium with strange, stretched qualities. Many predators struggle here because the rules of perception break down. Refraction shifts outlines. Light scatters, movement becomes ambiguous. But for the monkfish, this dim landscape is not an obstacle. It is an advantage. A monkfish lies buried beneath a thin sheet of sand, its body blending seamlessly into the substrate. Only two features remain visible, the wide, jagged outline of its mouth and the single fleshy lure rising from its head like a tiny flagpole in the murk. The rest of the fish disappears into the seafloor. To an untrained eye, it resembles a patch of uneven sediment. To prey, it is simply another piece of terrain. Nothing about its posture suggests movement or threat. This is precisely the point. The monkfish's survival depends on becoming the least notable object in a place already full of shadows and confusing shapes. Darkness, however, is not the monkfish's primary shield. Motionlessness is. The fish presses itself against the sand until its skin texture matches the surrounding grains. Sand filters around its fins and settles into tiny ridges along its back. Over minutes, the fish becomes indistinguishable from its environment. This camouflage is not static, it is continuous. Every shift in the current adds a few more particles to its outline, strengthening the illusion. Even when a fish swims directly above it, the monkfish is nothing more than a faint depression on the seafloor. Yet despite the darkness and its buried position, the monkfish is not blind. In fact, it perceives its surroundings with a resolution that rivals the sensory abilities of far more active hunters. The key lies in the lateral line system, a network of fluid-filled canals running along its head and body, each lined with sensory cells called neuromasts. These structures detect changes in water pressure and vibration with astonishing sensitivity. Where many fish require vision to track prey, the monkfish reads the underwater world through vibrations alone. In this environment, motion is everything. When a small fish darts through the water, it creates tiny pressure waves that spread outward like ripples. These waves travel in three-dimensional patterns, wrapping around rocks, bending over dunes of sand, and drifting into hollows. For most animals, these faint distortions are meaningless background noise. For the monkfish, they are a detailed map. When a shrimp flicks its tail several meters away, the monkfish senses the faint vibration long before anything else moves. When a small cod glides past, the wake of its fins produces a signature pattern the neuromasts can decode. The pressure changes allow the monkfish to determine not only direction and distance, but even the speed and size of the animal creating them. Each passing creature has a fingerprint of movement. The monkfish is not simply detecting vibrations, it is interpreting them with the precision of sonar. The lateral line system responds to frequency and amplitude. A rapid, high-frequency pulse might signal a small fish in panic. A slower, heavier distortion might indicate a larger animal cruising past. The monkfish lies perfectly still, reading these signals as if listening through its skin. Its sensory world is not constructed from light or shadow. It is built from shifting gradients of pressure. This transforms the seafloor from a flat, dark plane into a three-dimensional map of motion, where every ripple and tremor carries information. Despite its extraordinary ability to perceive vibrations, the monkfish does not rely solely on this system. It adds a second sensory channel, the esker, the lure suspended above its mouth. This fleshy appendage wiggles subtly, mimicking the motions of a small marine organism. In dim light or mild turbidity, it becomes a beacon of opportunity. Fish drawn to visual cues approach, believing they have stumbled upon easy prey. The monkfish never moves the rest of its body. Only the lure performs tiny twitches that appear almost accidental, as though grazed by a passing current. This combination of vibration sensing and passive luring is a powerful evolutionary strategy. The lure serves as the visual trigger. The lateral line system provides the moment of truth. When a curious fish swims close to investigate the wriggling esker, the monkfish tracks the pressure waves generated by each fin beat. It does not strike immediately. Instead, it waits for the precise moment when the prey enters the ideal sensory zone, the fraction of space in front of its mouth where water pressure gradients become tightly focused and easily interpretable. In that small region, the monkfish perceives motion with maximum clarity. The prey becomes not just a target, but a series of vibrational contours that define its exact position in three-dimensional space. Once the prey crosses into this zone, the monkfish commits. The strike is explosive, but startlingly short. The mouth does not simply open, it expands forward. Through a rapid expansion of the buccal cavity, the monkfish creates a powerful suction force. This vacuum pulls water and prey into its jaws faster than most fish can swim. The entire maneuver, from stillness to engulfment, unfolds in less time than a human blink. The lateral line system ensures accuracy even in complete darkness. The monkfish does not need to see the prey in the final instant. It senses the collapse of pressure waves as the target enters its strike radius. The concept of a blind predator is misleading. Although monkfish often reside in areas with minimal light, they are not disadvantaged by darkness. Vision plays a secondary, even tertiary role. The lateral line system receives information more quickly than the eyes could. Vibrations do not depend on clarity of water or presence of light. They do not scatter. They do not refract unpredictably. They travel cleanly, offering a stable means of perceiving the world. For the monkfish, this means the difference between passively waiting and actively selecting an ideal moment to strike. As the monkfish lies motionless, the seafloor around it pulses faintly with the movements of countless small organisms. A crab scuttles several meters away, sending out low, rolling vibrations. A small school of fish cruises just above the sand, their collective motion creating a combined pattern of wave fronts. To the monkfish, these patterns overlap yet remain distinguishable. Each pressure wave travels through the water like a separate thread in a woven fabric. The fish's neuromasts pick up the dominant patterns, filtering irrelevant signals the way a musician tunes out background noise to focus on a single instrument. The remarkable aspect of this sensory world is not just its detail, but its reach. Many species can detect threats only when they are dangerously close, reacting at the last moment. The monkfish identifies prey well before physical contact is possible, giving it time to prepare and position its strike. It can sense a fish drifting behind it, approaching from the side, or hovering cautiously in front. Unlike predators that rely on fixed forward vision, the monkfish experiences its surroundings as a spherical field of motion rather than a narrow beam of sight. This three-dimensional detection is what transforms the seafloor from a static background into a living, shifting network of information. Evolution shaped this animal not for pursuit, but for perfect ambush. Its body is wide and flattened, designed to spread weight evenly on soft sediments. Fins splay outward, providing stability rather than speed. The jaws occupy a disproportionate portion of its head, forming a trapdoor mechanism optimized for suction-based capture. Every adaptation supports the central theme: read the water, wait without moving, strike with absolute precision. The monkfish's ability to blend pressure sensing with visual baiting creates one of the most efficient hunting strategies on the seafloor. Its lure is not flashy, it is understated, offering just enough motion to attract attention without revealing the body beneath. Its lateral line system does the slow, meticulous work of interpreting the environment long before the prey realizes danger is near. Together, these systems give the monkfish mastery over a habitat where other predators struggle to navigate. In this dim underwater world, the monkfish turns sensory darkness into clarity. It transforms a sand-covered landscape into a radar-like grid of vibrations, reading movement with a level of nuance that seems almost unreal. What appears to humans as a blind, motionless fish is in truth a predator immersed in a flood of information, detecting motion long before any eye could see it. And with that information, The monkfish holds power in the silence of the seafloor, waiting with patience shaped by millions of years, ready to pull the next unsuspecting fish into the dark. The estuary at low tide looks deceptively calm. Mangrove roots rise like tangled scaffolding from the brackish water, their twisted limbs casting warped shadows across a glassy surface, broken only by drifting pollen and the slow roll of distant swells. In this stillness, the air feels heavy, thick with humidity, and the faint smell of rotting leaves. Fish ripple the shallows occasionally, sending faint concentric rings outward before the water returns to quiet. Most animals see only the obvious, a sheet of water, a maze of roots, a shifting play of reflection and shadow. But beneath this surface, motionless and almost completely invisible, lies a predator that interprets the world through an entirely different channel. The saltwater crocodile floats with nearly its entire body submerged, exposing only a small pair of nostrils and two eyes that protrude just enough to break the surface tension. Everything else, several meters of muscle, armor, and instinct, stays below the boundary between water and air, hidden in the dim green layer where sunlight dissolves into murk. To an observer, it appears lifeless, a piece of driftwood or a dark lump caught between mangrove roots. This illusion is deliberate. The crocodile's body is held in perfect stillness. No fin flicks, no tail sways. The water around it remains undisturbed. What appears to be a motionless animal is, in reality, a predator listening with its skin. Along the jawline and snout of the saltwater crocodile lie hundreds of tiny sensory organs embedded within specialized scales. These structures, called integumentary sensory organs, or ISOs, are small domes that detect pressure changes with remarkable precision. They resemble tiny dark freckles scattered across the thick armor plating of the crocodile's face, but their function almost defies belief. Each ISO contains a network of nerve endings, sensitive to even the faintest disturbances in water. A single raindrop landing on the surface, meters away, sends a subtle pressure wave that radiates outward. The crocodile feels it. This sensitivity is not broad or undefined. It is directional. When a small fish breaches the surface several body lengths away, the splash sends out pressure waves at specific frequencies. ISOs interpret the pattern, allowing the crocodile to determine the size of the fish, its location, and even the direction of its movement. A wading bird dipping its beak into the water produces a different pattern, lighter, sharper, with a distinct signature. The crocodile perceives these signals not as random vibrations, but as structured information. Pressure waves move through water with greater clarity than light in murky estuaries, and the crocodile's sensory system is optimized to interpret them instantly. This means that the crocodile does not rely on sight to detect prey. Vision is merely a secondary tool. The true trigger for a strike is pressure. As the crocodile floats in the shallow water, its internal posture is one of readiness rather than relaxation. Muscles remain taut beneath the surface, but without movement. A perfect ambush depends on not signaling presence. Prey in mangrove environments has learned through evolution to fear shape and motion, but pressure detection remains a far more subtle cue. The crocodile's body blocks almost no current. It resists the urge to adjust or drift sideways. Even its breathing becomes controlled. Each inhalation and exhalation moves only the nostrils above the waterline, never the bulk of the submerged body. In this suspended state, the crocodile experiences a world far different from our own. While humans depend heavily on vision to interpret their surroundings, the crocodile constructs a three-dimensional map from pressure alone. It feels a mullet flicking nervously in the weeds. It senses the soft footfall of a heron stepping into the shallows. It detects the pressure displacement of a mud crab climbing between roots. Every disturbance sends ripples across the surface. The crocodile feels these as geometric patterns that connect it to the movements of other animals long before those animals become aware of its existence. This ability becomes especially powerful near the surface, where the boundary between air and water creates a unique medium for pressure transmission. When a bird lands on the water, its feet slap the surface, producing a signature that ISOs pick up instantly. When a fish leaps briefly into the air and splashes down, the water flexes at the point of contact. The crocodile tracks these disturbances without ever lifting its head. Even the soft drip of mangrove leaves falling into the water is registered, each drop adding a layer of sensory texture to the environment. Despite myths of crocodiles relying solely on opportunistic lunges, their hunting strategy is far more deliberate. They are not simply watching, they are interpreting. ISOs function like a radar array stitched into the skin. The crocodile triangulates disturbances using multiple receptors across both sides of the jaw. With each wave of pressure, it refines the position of prey in three-dimensional space. Light may scatter and break on the surface, but pressure does not lie. The true artistry lies in the crocodile's ability to remain completely still while processing this information. Stillness is essential. The moment the crocodile moves, it distorts the water around its own body, producing pressure waves that interfere with incoming signals. Ambush success depends on preserving a perfectly neutral hydrodynamic footprint. Long minutes pass, sometimes hours. The crocodile waits, relying on an ancient, energy-efficient strategy that wastes almost nothing. Then, the right pattern arrives. A fish breaks the surface in a brief, panic-driven jump. The splash creates a sharp displacement, sending fast, high-frequency pressure waves outward. The crocodile interprets them instinctively. Weak amplitude, small body, erratic movement. Not worth a full strike. The predator remains still. Moments later, a much different vibration cascades across the mangrove pool. A large bird lands clumsily on a partially submerged root, sending a deeper set of waves curling across the water. These lower frequency waves carry more mass behind them. The crocodile senses the bird's exact location, the slight shift in balance as it folds its wings, the delicate tremor of its legs as it adjusts its stance. These details reach the predator with astonishing speed. Pressure transmission through water is nearly instantaneous compared to visual interpretation. The crocodile decides. The strike mechanism begins before the body moves visibly. Beneath the surface, muscles along the torso tense, building potential force. The tail shifts ever so slightly, though the movement is so small it barely generates turbulence. This micro-adjustment lines the body into an attack vector aimed exactly along the pressure gradient that corresponds to the prey's position. The crocodile does not look first. It does not need to confirm with its eyes. The pressure pattern is enough. Suddenly, the calm water erupts. The crocodile explodes forward with a burst of acceleration that belies its massive size. Its jaws break the surface in a violent surge of power, closing around the prey's position with shocking accuracy. The bird has barely begun to react when the crocodile's jaws snap shut. The precision of this strike is no coincidence. It is the predictable outcome of a sensory system that interprets the slightest movement in the surrounding water. After the strike, the crocodile often sinks back into the water without struggle, constricting its jaws to maintain grip before dragging the prey under. The violent moment is brief, but the preparation behind it is long and calculated. This pressure-based hunting strategy offers advantages that few other predators possess. It functions in complete darkness. It works in murky water, where visibility drops to near zero. It remains effective even when prey is partially obscured by vegetation or shadow. The crocodile does not need to see the prey. It needs only to feel the water deform. These sensory abilities extend beyond hunting. Young crocodiles use pressure sensing to locate their mother in dense reeds. Adults perceive weather changes through shifts in water movement. Even the flowing tide carries information they can interpret using their ISOs. It is a subtle, complex language of pressure and displacement, a form of perception many animals simply cannot access. In the still waters of estuaries, where vision falters and motion becomes ambiguous, the saltwater crocodile sees with its skin. It interprets the world as a tapestry of vibrations, reading ripples the way a skilled tracker reads footprints. Hidden beneath the surface, it waits for the one pressure pattern that signals opportunity. And when that moment comes, the strike is already decided. The coastal sea looks calm from above, but beneath the surface the world churns with invisible motion. Tides push and pull through kelp forests. Sand swirls in complex spirals, and schools of fish carve tunnels of turbulence that collapse into long, fading trails. In this dynamic environment, most predators rely on vision to hunt, peering through beams of light that shimmer down from the surface. But in the grey-green waters favored by harbour and grey seals, visibility shifts constantly. Waves distort shapes, sediment clouds the water column, sunlight fractures into glittering patches that blur outlines. Chasing prey by sight alone is a losing strategy. Instead, seals turn to a sensory system of such exquisite precision that it borders on the extraordinary. For these marine mammals, the key to survival lies not in what they see, but in what their whiskers feel. A seal glides effortlessly through the murk, its body streamlined like a torpedo, but its head surprisingly delicate. Long whiskers trail from its muzzle, not loose, fluttering hairs, but firm, sculpted structures that curve slightly backward. These whiskers, called vibrissae, are among the most sensitive biological sensors in the ocean. Each whisker is embedded deeply in the seal's skin, surrounded by a complex sheath of nerves and blood-filled sinuses capable of detecting minute hydrodynamic changes. They are so sensitive that a seal can detect the movement of a single tiny object passing meters away, even when the object never touches the whisker itself. The entire sensory system is designed to interpret the flow of water, turning fluid turbulence into a detailed map of movement. This ability is most dramatic when seals track the ghost wakes left behind by fleeing fish. When a fish swims, it pushes water backward with each tail beat, leaving behind a trail of vortices, swirling rings of disturbed water that form a hydrodynamic fingerprint. These vortices persist for minutes, slowly weakening as turbulence dissipates. To most animals, these ghost wakes are undetectable once the fish is out of sight. But to a seal, the wake is as clear as a neon trail across the sea floor. Its whiskers pick up the tiny eddies, and pressure changes left behind, allowing it to follow the fish long after the prey has vanished into the murk. The secret lies in the shape of the whiskers themselves. Most mammals have cylindrical whiskers that vibrate when moved through air or water. These vibrations create noise, self-induced oscillations that can drown out subtle external signals. But seal whiskers evolved a unique, undulating geometry. Instead of being smooth and straight, each whisker has a wavy, flattened profile resembling a serrated ribbon. This unusual shape disrupts the formation of regular vortices as the seal swims, dramatically reducing whisker self-motion. Without this self-generated noise, the whiskers can remain perfectly still, even as the seal accelerates or changes direction. This stillness allows them to detect external turbulence with exceptional clarity. Evolution sculpted these whiskers into tools of hydrodynamic stealth. When a seal hunts, it does not swim blindly. It glides silently, whiskers splayed forward like antennae. These whiskers do not simply brush against the water, they read it. Each hair responds to minute changes in flow, velocity, and direction. The nerves at the base of each vibrissa are arranged in clusters with different directional sensitivities. When a passing vortex pushes against the whisker, the pattern of nerve activation reveals the shape, strength, and orientation of the disturbance. The seal's brain takes these signals and reconstructs a three-dimensional picture of the wake, identifying the type of animal that made it and estimating how long ago it passed. A fleeing fish leaves behind a series of alternating vortices, forming what scientists call a Kármán vortex street. The size of these vortices corresponds to the fish's body width. Their spacing reveals the rhythm of the tail beats. Their decay reveals how long it has been since the fish swam through. A seal interprets all of this instinctively. It knows whether the prey was small or large, moving quickly or hesitantly, turning left or right. And unlike vision, which loses detail with distance and clarity, hydrodynamic trails persist in the water long after light has failed. Imagine a landscape of invisible trails winding through the sea, twisting, curling, drifting slowly upward, or dissipating into silence. This is the world the seal perceives. It navigates through these ghost pathways the way a hunter might track scents across a forest. When the seal finds a trail, it adjusts its course with precision, not by seeing the fish, but by reading the turbulence left behind. It follows the trail downstream, whiskers twitching as new vortices brush past. The seal can tell when the wake intensifies, when the prey has turned sharply, when it slowed momentarily, or when it accelerated in panic. The richness of this hydrodynamic information is extraordinary. But seals do not merely react, they predict. As they follow a trail, they anticipate where the prey will go next. Fish fleeing in panic often swim in irregular paths, zigzagging or looping. The seal reads these deviations in the wake and adjusts accordingly. Even if the fish gains distance, the hydrodynamic ghost wake remains intact. The seal uses these trails like a map, pursuing the prey even through murky or dark waters, where vision is nearly useless. The sensitivity of seal whiskers extends beyond hunting. Seals can detect underwater objects without seeing them. They can avoid rocks in low visibility by sensing small currents created as water flows around them. They quickly learn to identify the hydrodynamic signatures of predators, such as the distinctive wave patterns created by orcas moving through narrow straits. Even stationary objects create slight deflections in water currents that a seal's whiskers can interpret. For these animals, the ocean is not a blank blue space. It is a dynamic field of motion shaped by every creature and structure. The neural processing behind this ability is equally remarkable. The part of the brain responsible for interpreting whisker signals is extremely large compared to other marine mammals. Each whisker sends a torrent of data at high speed, and the brain must analyze multiple whiskers simultaneously to construct a cohesive picture. This requires integrating information across a wide array of frequencies and directions. It is a level of sensory processing closer to that of a sophisticated instrument than a typical mammalian system. Unlike predators that rely on bursts of speed, seals do not need reckless acceleration. Their hunting efficiency comes from certainty. Instead of sprinting blindly toward a distant splash, they move with calm purpose, guided by an invisible trail only they can sense. The precision of their whiskers means energy is not wasted. They close distance intelligently, not chaotically. When they finally reach the prey, the final chase may last only seconds, but the real work has already been done, in the minutes spent reading the ghost wake of a fish that believed it had escaped. In clear water, vision still plays a role, but seals never depend on it alone. Even in perfect visibility, they combine sight with hydrodynamic sensing, confirming through whisker input what they perceive visually. If a fish disappears into a cloud of silt or darts behind a kelp frond, the seal does not lose track. It simply follows the turbulence. Vision becomes supplementary. The whiskers remain primary. In winter, when storms churn the coast and sediment fills the water column, seals are not disadvantaged. Their ability to track wakes becomes even more valuable. While other predators abandon shallow hunting grounds filled with silt, seals move confidently through the dark, guided by vortices sculpted by creatures they cannot see. This allows them to exploit feeding opportunities in conditions that exclude competitors. Seals inhabit a world defined by motion. Every beat of a fish's tail, every swirl of a crab moving along the bottom, every flutter of a bird diving, all of it leaves hydrodynamic signatures in the water. These signatures drift through the sea like fading memories, and seals, with their exquisitely evolved whiskers, retrieve these memories effortlessly. To a human diver, the water may appear empty. To a seal, it blazes with trails. Invisible lines of turbulence branch and weave, a shifting network of movement left behind by the living world. A hunt does not begin with the sight of prey. It begins with the whisper of a vortex brushing against a whisker, a ghost wake pointing to life just beyond the reach of light. The Arctic shallows are a place of contradictions. Above, the world is a clean palette of white snow, blue sky, and drifting ice flows. Below, the water is a shifting brown haze, thickened by suspended mud and organic debris. The seafloor here is soft, almost gelatinous, a mixture of silt and decaying materials stirred constantly by tides and storms. Visibility often collapses to nothing. Even a few fin strokes can turn the water column into a swirling cloud of darkness. This turbid world might appear hostile to any predator that depends on vision or speed, but it is the perfect hunting ground for an animal built to sense through touch rather than sight. In these shallow Arctic waters, the walrus feeds not by chasing moving prey, but by detecting the subtle presence of clams hidden beneath layers of sediment. A task made possible by one of the most remarkable sensory systems in the marine world. A walrus descends slowly, its immense body sinking into the dim water, while its foreflippers angle outward like stabilizers on a submarine. The moment its snout nears the bottom, the true machinery of its perception emerges, a dense forest of whiskers, nearly 1,000 in number, radiating outward in a stiff, bristling halo. These whiskers, or vibrissae, are thick, muscular, and surprisingly hard. Not fine hairs like those of a seal, but short, stout sensors capable of pushing through gritty sediment without bending. Each vibrissa is connected to an elaborate follicle filled with blood sinuses and nerve endings, and each follicle communicates with the brain in fractions of a second. The walrus does not simply have whiskers. Its entire muzzle functions like a tactile scanning array, capable of detecting minute differences in shape, density, and texture. The walrus does not look for clams. It feels for them. When its face meets the seafloor, the whiskers push downward, sweeping in small arcs, probing the mud like hundreds of fingertips. The animal moves slowly and deliberately, pressing its entire snout through soft layers that obscure everything from view. In murky Arctic shallows, vision becomes useless the moment the animal begins feeding. But a walrus does not rely on vision at all. It dives into complete blindness willingly, knowing that the sediment around it contains everything it needs to locate its prey. Buried beneath the mud are bivalves, clams, mussels, and other shellfish, packed densely into the Arctic substrate. They do not move quickly, nor do they flee when approached. Evolution armed them with shells, not speed. But those shells, despite being hidden beneath layers of sediment, provide the walrus with exactly the tactile signature it needs. Hard surfaces reflect mechanical pressure differently from soft mud. Even a small clam responds to contact by shifting just slightly, producing a mechanical contrast that the walrus's whiskers detect instantly. These differences are so subtle that most creatures could not perceive them. The walrus reads them effortlessly. The walrus's vibrissae are arranged in organized rows, each with slightly different lengths and orientations. This arrangement gives the animal a layered sensory field, allowing it to scan the seafloor in 3 dimensions. As the whiskers press downward, they splay apart, increasing surface coverage. Each whisker moves independently, responding to disturbances or resistance. Where one whisker meets soft mud, another might contact a buried shell. This combination of simultaneous inputs creates a detailed tactile map. The walrus interprets this map with precision equal to human fingertips, brushing across braille. But touch is not the only sense the walrus engages. As it digs with its whiskers, it stirs up clouds of sediment, which release subtle chemical cues into the water. Buried clams excrete small amounts of metabolic byproducts, and these traces become suspended in the tiny plumes of disturbed mud. The walrus can detect these faint chemical signals directly through the sensitive tissues of its snout. It is not smelling in the human sense. Underwater, this process functions more like direct contact chemoreception. The animal blends tactile and chemical signals into a combined sensory strategy. Where touch confirms hardness and shape, chemical cues confirm life. Once the walrus identifies a buried clam, the real feeding behavior begins. Its vibrissae guide the snout to the exact spot. Then the walrus uses a technique that is as efficient as it is surprising. It creates suction powerful enough to extract the clam from the sediment. By contracting muscles in the throat and cheeks, the walrus forms a vacuum that pulls water and the prey directly into its mouth. This suction is so strong that it can remove the flesh from a clam's shell without breaking it. Archaeological sites near former walrus hunting grounds often contain piles of intact, empty shells, evidence of this suction feeding technique practiced for thousands of years. Suction feeding is biologically expensive. It requires precise control of the mouth and throat muscles, but it allows the walrus to consume large quantities of clams in a single dive. A single feeding event might involve dozens of rapid suction pulls, each one extracting a clam that the walrus located through tactile scanning alone. The efficiency of this system is astonishing. In near-zero visibility, this massive marine mammal can gather food with higher accuracy than many visually dependent predators in clear water. The walrus's sensory world is not limited to detecting clams. As it moves across the seafloor, its whiskers respond to everything. The presence of rocks, the ripple marks left by passing currents, the trails left by benthic invertebrates, and the subtle vibrations created by other animals burrowing nearby. Each whisker acts like a pressure sensor, detecting resistance patterns created as water flows around objects. Hard objects produce sharp, defined currents. Soft organisms produce diffuse, gentle disturbances. The walrus interprets these patterns the way a skilled forager might interpret footprints on snow. The density of nerve endings in each vibrissae follicle rivals that of some primate fingertips. This is not a feature found in other large marine mammals. The walrus's entire feeding strategy depends on reading the seafloor with tactile clarity unmatched in the Arctic. Without this system, the turbid shallows would be a barren environment. With it, the walrus gains access to vast stores of buried energy reserves in the form of shellfish colonies. As the walrus continues along the bottom, it moves slowly, sometimes turning sideways to press more whiskers into the sediment, sometimes rotating its head slightly to maximize tactile coverage. The animal is not guessing, it is gathering data. Every movement of water around an object provides information. Every object pressed by a whisker reveals its composition. Even when the water becomes filled with silt and organic debris so thick it resembles wet smoke, the walrus remains unbothered. It has effectively gone blind by choice, entering a world where its face becomes the primary sensory organ. The Arctic shallows undergo constant change. Tides shift sandbars. Ice chunks drift overhead and scatter noise through the water. Storms send surges of sediment sweeping across the bottom. Yet even in this unstable habitat, the walrus finds consistency through touch. Clam beds cluster in predictable areas where organic material settles. Walruses return to these feeding grounds year after year, guided not by memory of how things looked, but by how the sea floor felt. When other predators face darkness or murk, they struggle. Vision becomes useless. Echolocation becomes unreliable near sediment. Chemical signals become diluted. But the walrus thrives precisely because the conditions reduce competition. Few predators can access food buried beneath thick mud. Fewer still possess the sensory tools to detect clams buried deep below the surface. The walrus's giant body and armored hide may seem imposing, but its real advantage lies in the delicate sensitivity of its whiskers. Each dive reveals the walrus's sensory brilliance. It moves with intentional slowness, every sweep of its face adding to its tactile understanding of the world. Instead of sharp eyes or advanced sonar, it relies on thousands of finely tuned touch receptors. Where humans might see nothing but brown haze and darkness, the walrus perceives a detailed landscape filled with hidden shapes. To this animal, the mud is not an obstacle. It is a medium of information. The walrus rises from the sea floor with its mouth full, pushing upward through swirling silt. Behind it, the impression of its whiskered muzzle remains for a moment on the disturbed bottom. The animal surfaces briefly, expelling a breath of air into the cold Arctic sky, then dives again, returning to its sensory realm below. In the shadows of polar waters, where vision fails and light vanishes, the walrus navigates with effortless precision. Its face is not merely a tool, it is an entire sensory platform, an armored array of tactile detectors capable of turning a muddy seafloor into a grid of hidden signals. Where others see darkness, the walrus feels clarity. Where others hesitate, it moves with confidence. In the Arctic shallows, the walrus does not search for food by sight, sound, or scent. It reads the seafloor itself, one whisker at a time. The water over a seagrass meadow is often described as clear, but clarity is deceptive. Even in bright sunlight, the shallows glow with fine suspended particles, drifting sediment, fragments of algae, clouds of tiny invertebrates stirred up by tides. These meadows breathe with the rhythm of currents, bending and straightening in long green waves that obscure the bottom. Visibility shifts from moment to moment. A passing stingray sends plumes of silt spiraling upward, and the meadow becomes a fog of drifting green and brown. For most grazing animals, such turbidity would be an obstacle. For the dugong, it is merely the background of a sensory world shaped not by sight, but by smell and touch. A dugong moves across the meadow with slow, deliberate strokes of its paddle-shaped tail. Each movement seems careful, conserving energy, as though the animal is reading the water with its entire body. Its silhouette is rounded, gentle, almost soft. But the head tells a different story. The snout bends downward, almost shovel-like, designed for a life spent close to the seafloor. The upper lip is muscular and prehensile, lined with stiff bristles that act like tactile probes. When the dugong lowers its face into the meadow, the snout becomes its primary sensory tool. The animal is not searching with its eyes. It is feeling and tasting the meadow one blade at a time. Seagrass meadows are patchy environments. Some areas explode with fresh, tender shoots, rich in nutrients. Others wither or rot after storms, grazing, or sediment deposition. Chemical signals drift through the water, carried by microcurrents around each blade. Dugongs detect these signals through specialized tissues in their nasal passages and mouth. This chemical sense is subtle, more akin to tasting dissolved molecules than smelling them in air. But for a dugong, the difference is profound. These cues reveal whether the grass ahead is fresh, damaged, or decaying. As the dugong grazes, it sweeps its snout across the bottom, brushing seagrass blades with its bristles. Each bristle bends in response to contact, sending tactile information to the animal's brain. The stiff, whisker-like structures at the tip of the upper lip allow the dugong to differentiate between healthy blades, new shoots, coarse, mature stems, and root structures beneath the sediment. It can identify the orientation of growth, the thickness of rhizomes, and the density of a patch. This tactile sensitivity helps the dugong choose the most nutritious parts of the meadow while minimizing wasted effort. It does not simply mow the grass, it selects with precision, but the dugong's sensory world extends deeper. When it grazes, it uproots sections of the meadow, exposing sediments and stirring silt into the water column. This disturbance releases chemical cues trapped within the substrate. Fresh roots emit a different molecular signature than decomposing ones. Sediment with active plant growth smells different, in a chemical sense, than sediment that has been smothered or damaged. Dugongs follow these gradients, using them to locate patches where seagrass is regenerating. These patches often form after storms or disturbances open new space for shoots to emerge. The dugong becomes not only a grazer, but a selector of the meadow's healthiest, most productive zones. In this process, the dugong's feeding behavior shapes the ecosystem more deeply than many observers realize. By feeding heavily on certain patches while avoiding others, dugongs create gaps in mature grass beds. These gaps are not random. Dugongs often return to areas where the chemical cues signal fresh, tender growth. When they feed, they remove older stems and roots, loosening sediment in a way that encourages new shoots to take hold. This creates a mosaic of grazed and ungrazed sectors, a patchwork that helps maintain the meadow's biodiversity and productivity. To the dugong, the meadow is not a uniform field of green. It is a textured chemical landscape containing subtle gradients that indicate age, health, species composition, and recent history. Some areas feel right, soft, fresh, rich in new blades. Others feel wrong, coarse, sour, overgrown, or decaying. Dugongs avoid those places, and their avoidance shapes how the meadow recovers. Meadows grazed lightly and consistently tend to be younger, more productive, and more resilient. Meadows left ungrazed for long periods develop dense canopies that can shade out new growth, becoming less nutritious over time. Dugongs through their sensory-driven feeding, keep meadows young. As the dugong glides onward, the water around its face resembles a slow-motion explosion of tiny particles. Sediment rolls upward in clouds, drifting back down like snow. If a human diver entered this scene, vision would drop to near zero. Yet the dugong continues unbothered, probing the bottom with its bristled lip, lifting and tasting blades one after another. It detects whether a blade has been grazed previously, whether a patch is recovering, whether a root holds strong or is weakened by decomposition. These details form the dugong's mental map of the meadow. A map drawn not from sight, but from touch and chemical gradients. The mouth of a dugong is remarkably specialized. The lips form a muscular pad capable of manipulating seagrass like a hand. When the dugong feeds, it grips entire swaths of grass with this pad, then tears them free with a downward jerk of its head. Each tear releases mechanical and chemical cues that continue to guide its feeding decisions. If the patch yields easily and tastes fresh, the dugong continues. If the patch resists, contains coarse stems, or gives off signals of decay, the dugong moves on. Chemosensory ability plays a deeper role still. As the dugong breathes underwater, it closes its nostrils, but surface breaths allow it to sample the water's chemical composition indirectly as traces cling to the snout. Seasonal changes in temperature and currents alter the distribution of seagrass species across the meadow. The dugong detects these shifts without needing to see them, following scents toward areas where certain species flourish. Some seagrass species are richer in nitrogen or carbohydrates, providing higher energetic value. Others are tougher, fibrous, less palatable. The dugong's chemical senses help it tune its grazing to maximize energy intake. This grazing behavior contributes to the health of the entire meadow. When dugongs remove older growth, they reduce shading and allow more light to penetrate the seafloor. Their foraging pits expose buried seeds and rhizomes, stimulating sprouting. Areas once smothered in sediment become oxygenated as the dugong stirs the bottom. Even their feces enrich the meadow, depositing nutrients directly into the sediment where new shoots are forming. Where dugongs exist in stable numbers, meadows tend to regenerate faster after storms or heat events. But perhaps the most fascinating aspect of the dugong's sensory life is the integration of touch and smell into a unified perception. Unlike predators that rely on echolocation or pressure detection, the dugong's world is tactile and chemical, intimate and immediate. It feels its environment continuously, not passively. Every motion of its snout brings new information. Its sensory world is slow, steady, and quiet, a contrast to the rapid sensory processing seen in predators. This slowness is not a disadvantage. It is an adaptation to a life spent in the calm edges of the sea, where patience and precision yield abundance. The meadow shifts as the tide rises. Sunlight becomes muted. The blades sway more quickly. Tiny fish dart between the stems, hidden from view by drifting sediment. The dugong continues its slow path, snout buried in the grass, whiskers flexing with each contact. It is following a gradient of freshness, drawn by the faint chemical cues of new growth. Its feeding trail forms a visible trench behind it, a clean, neatly cleared lane cutting through the meadow. Days later, that trench will be filled with new shoots. Weeks later, it will be indistinguishable from the rest of the meadow, refreshed by the dugong's grazing. For the dugong, the seagrass fog is not a barrier, but a guide. Touch reveals texture. Taste reveals freshness. Chemical cues reveal regeneration. Sight in this world is merely decoration, useful at times, unnecessary for survival. The dugong swims onward, carving its sensory map with each brush of its snout, shaping the meadow with every mouthful. It does not see the landscape it builds. It feels it. The far south begins with brightness. The ice reflects the sun with almost metallic intensity, turning the horizon into a white blaze that erases shadows and overwhelms color. The line between sky and snow dissolves, and even the faintest movement becomes difficult to distinguish against this blinding backdrop. In this environment, where glare cuts across the surface like blades of light, most animals must squint or turn away. Penguins, however, face it directly. They waddle across ice fields under conditions that would cripple human vision, then plunge into cold water, where the world shifts instantly from searing white to shadowed blue. To survive in such a reality, penguins rely on a visual system that functions like two sets of eyes in one skull, one optimized for an overexposed, high-glare surface world and one built for the dim, blue-shifted depths below. On land or ice, penguins navigate a landscape dominated by brightness. Light scatters off snow crystals, reflecting in all directions. The sun sits low across much of the year, creating long bands of optical distortion. Penguins counter this with specialized adaptations in the cornea and retina that reduce scatter and sharpen edges. Their cornea, flatter than that of many birds, helps offset the intense refractive index between air and water. More importantly, their retina contains a dense distribution of cones capable of handling extreme brightness by adapting quickly to floods of light. They do not become dazzled in the same way humans do. Their pupils constrict rapidly, forming narrow slits that limit incoming light and reduce glare. Yet penguins do not merely tolerate this brightness, they use it. The surface world's glare carries polarized light patterns, especially around the sun's position. Penguins detect these polarization angles with specialized photoreceptors, allowing them to maintain a sense of direction even when the horizon disappears in white haze. This gives them a rudimentary navigational compass, allowing them to orient toward feeding sites, breeding colonies, or openings in the ice. Above water, their vision becomes a tool for large-scale orientation rather than detail. In this overexposed realm, they do not need to see fine textures. They only need to interpret brightness gradients and polarization cues. Then the penguin dives, and the world transforms. Cold water envelops its body, and the surface glare vanishes instantly. Light becomes diffuse, filtering in from above in a soft cobalt glow. Colors fade with depth. Reds disappear first. Yellow and green last only a little longer. What remains is a world of blue and shadow, where fish and krill appear as dark silhouettes darting through open water. In this environment, penguins must shift visual modes completely. Their lens, unusually flexible for a bird, adjusts its shape rapidly to maintain sharp focus underwater. Unlike terrestrial birds, whose eyes function primarily in air, penguins evolved a lens that compensates for the optical flattening effect of water. The moment they submerge, the lens thickens, and the penguin achieves the kind of underwater acuity that rivals marine mammals. Underwater vision demands speed, more than brightness tolerance. Fish and krill move in bursts, accelerating unpredictably through columns of light. Penguins track these targets using a method similar to raptors, rapid, small head movements. These movements allow them to refine visual contrast, comparing edges and silhouettes from multiple angles in quick succession. The result is a three-dimensional reconstruction of prey position, even in murky or low-light conditions. Their eyes, positioned slightly to the sides of the head but angled forward, offer overlap that grants depth perception, essential for calculating the interception path during a chase. The underwater world amplifies contrast rather than sharp detail. Krill swarm in dense clusters, their movement creating shimmering clouds as they scatter incoming sunlight. Penguins rely on this shimmer to differentiate prey from the darker background. They do not track every individual krill. They lock onto moving boundaries within the swarm. For larger prey, like fish or squid, penguins rely on the crisp silhouette produced by lateral light, using their rapid head flicks to isolate the prey's outline from ambient motion. The cold water enhances this sensory clarity. As temperature drops, noise in the penguin's visual system decreases. Neural signals transmitted from the retina to the brain become sharper, more reliable. This physiological benefit allows penguins to hunt effectively, even in the dimmest hours of polar dusk. Humans might assume darkness hampers vision, but penguin eyes exploit what little light exists, converting faint blue photons into actionable information. As the penguin accelerates underwater, visual demands intensify. Speed compresses reaction time. A hunting penguin may reach velocities that rival some fish species, requiring split-second judgment. The penguin's eyes remain steady, even as its body twists and turns. Specialized ocular muscles stabilize the gaze, ensuring the retinal image remains sharp despite these rapid maneuvers. Without this stabilization, the world would blur during every stroke. Instead, penguins see clearly even in the midst of high-speed pursuit. But this clarity is not absolute. At certain depths, light becomes scarce. The penguin must rely on silhouettes. Here again, their retinal design helps. Rods, the photoreceptors responsible for low-light vision, dominate large sections of the retina. This rod-rich arrangement gives penguins superior sensitivity to motion and shape in near darkness, though at the cost of color discrimination. For penguins, however, color is secondary. Motion and contour drive hunting. When the penguin chases a fish, it does not simply swim behind it. It angles its body to intercept the fish's path, adjusting based on subtle shifts in contrast. A fish turning slightly appears as a change in silhouette thickness. A krill swarm contracting creates a shift in brightness at the edges. By interpreting these micro-changes, penguins anticipate movement and strike with precision. Their vision underwater is not passive, but predictive. Back at the surface, the penguin bursts upward into a world of glowing white. The eyes must adapt almost instantly. Upon emerging, the pupils constrict. The cornea resumes its air-optimized refractive function, and the retinal neurons adjust to brightness levels several magnitudes higher than below. Penguins achieve this transition with remarkable efficiency, switching sensory modes nearly instantaneously. Few animals on Earth navigate such dramatic changes in visual environment with equal ease. This dual visual world, blinding white above, shadowed blue below, defines the penguin's survival. It shapes their behavior, their hunting strategies, and even their internal navigation. When returning from long foraging trips at sea, penguins use the polarized light of the setting or rising sun to orient toward shore or breeding sites. The cues from polarized patterns are especially reliable during times when the horizon blends with the ice. These patterns guide them across long distances with surprising accuracy. In icy weather, blowing snow can erase visual landmarks entirely. Yet penguins still find their way. The glare from fresh snow scatters light horizontally, while older snow refracts it differently. Penguins detect these subtle distinctions, interpreting them through instinct and practice. Their world is defined by light's behavior, both underwater and above it. Although penguins cannot rely on color to the same degree as many tropical birds, they do not need it. Their environment provides information through contrast, motion, and polarization. Their eyes evolved not for aesthetic beauty, but for function under the most extreme visual conditions on the planet. Evolution shaped them into animals capable of switching between two optical realities: a bright, unforgiving world of ice and a dim, shifting world of underwater shadows. A penguin dives again, leaving behind the blinding white realm for the deep cobalt beneath. The shift feels instantaneous. Where one world dazzles, the other softens. Where one blinds, the other reveals. The penguin's eyes adjust effortlessly, lenses reshaping, retinas recalibrating, pupils widening. The fish below scatter in branching lines of motion. The penguin tilts its head, flicking rapidly in minute angles until a single silhouette sharpens. Then it accelerates, slicing through water, guided by the underwater world's crisp contrasts. Two sensory universes, one animal. Above water, penguins navigate a glare-filled realm of ice and reflection, reading polarized light like a compass. Below water, they enter a world of dim blue, where silhouettes and motion become their guiding language. In this duality, penguins hold mastery over two visual worlds, switching between them in the time it takes to break the surface. The octopus does not enter its world. It flows into it. Slipping from one crevice to another, its body reshapes itself without hesitation. 8 arms gliding over rocks, coral, sand, and algae. In the dim light of the reef, or the shadowed underhang of a rocky platform, nothing about the octopus moves carelessly. Every surface touched, every object brushed, every grain of sediment filtered between the suckers becomes information. And unlike almost every other animal on the planet, this creature does not keep sensation confined to a central brain. Its entire body, arms, skin, suckers, pigment cells, and outer layers, functions as a distributed sensory network capable of acting independently from the head. To the octopus, the environment is not merely perceived, it is experienced through an expansion of the self. An octopus's arm is not just a limb. It is a thinking extension, a semi-autonomous entity that can interpret stimuli, solve simple problems, and initiate actions without waiting for orders. Each arm contains its own neural cluster, a dense braid of neurons that rivals the complexity found in some vertebrate brains. These neural clusters control thousands of muscular fibers and hundreds of suckers, giving each arm incredible independence. Decisions such as grab, hold, release, or avoid can occur entirely within the arm's neural circuitry. The octopus's central brain remains informed, but it does not micromanage. It delegates. The true sensory marvel lies within the suckers. Each sucker is lined with dense fields of chemoreceptors and mechanoreceptors, cells that detect chemical signatures and physical textures. These receptors allow the octopus to taste through touch. When an arm glides over a shell, the suckers detect calcium carbonate and organic residues. When it brushes an algae patch, it identifies the chemical traces that define species and health. When it runs across the rough exoskeleton of a crab, it tastes proteins, lipids, and the faint chemical signals of stress the crab releases. The arm interprets this information within milliseconds. If the chemical profile matches food, the arm may tighten reflexively. If it matches something toxic or unpalatable, the arm withdraws long before the octopus's central brain receives full sensory input. This distributed decision-making means an octopus can be exploring 3 surfaces at once, tasting 3 different chemical environments, while its central brain focuses on camouflage, predators, or navigation. Its body acts like a swarm of cooperating processes, each solving its own micro-task in real time. This is not chaos. It is coordinated autonomy. The octopus's tactile world is extraordinarily rich. Its arms do not simply feel pressure, they decode complex textures. The arrangement of tiny ridges on a clamshell, the soft oscillation of sand disturbed by a buried shrimp, the direction of water flow over a rock cavity. All of these are interpreted instantly. The suckers can grip with both delicacy and force, able to peel apart fragile structures or wrench open dense shells. Every sucker operates almost like a fingertip, combined with a taste bud and a tiny decision-making center. Yet even this remarkable sensory capability is only part of the octopus's extraordinary sensory world. The skin itself participates in perception. Embedded across the octopus's body are proteins called opsins, the same types of light-detecting molecules found in eyes. These opsins allow the skin to sense brightness, and in some species, even basic contrast. While the octopus is not literally seeing shapes with its skin, it is detecting changes in light intensity across its body surface. This allows camouflage decisions to be made locally. A patch of skin sensing bright light stimulates chromatophores to expand or contract, altering pigmentation in that specific area without requiring the central brain to calculate every detail. This means an octopus's camouflage is not a top-down command, where the brain tells every patch what to do. It is a bottom-up collaboration, where each region of skin adjusts to local light conditions, creating an instantaneous, seamless cloak that perfectly matches the environment. Even when an octopus is injured, detached skin patches still react to light, suggesting that the sensory function is truly decentralized. No other animal on Earth uses its body in this way, as a living, responsive canvas capable of interpreting the world and adjusting in real time. Underwater, light is inconsistent. Sunbeams scatter, shadows cling to surfaces, and turbidity changes minute by minute. Fish rely on eyes. Crustaceans rely on antennae. But the octopus relies on everything at once. Arms tasting, suckers probing, skin detecting brightness, mantle interpreting water flow. These overlapping sensory systems allow the octopus to become nearly invisible. When it crawls across mottled rock, chromatophores mimic speckles and blotches. When it glides across smooth sand, pigments flatten and soften. When it hides in kelp, arms curl into leaf-like shapes and skin papillae erect to produce three-dimensional textures. The skin's light-sensing opsins refine these changes with localized accuracy, impossible for a centralized nervous system. Beneath this sensory avalanche sits the octopus's central brain, a structure that wraps around the esophagus and hosts vast neural density. But even this brain does not operate like the brains of vertebrates. It does not store hierarchical control. Instead, it orchestrates, coordinating wide-scale maneuvers, deciding when to flee or attack, guiding movement across larger distances. It leaves the fine details, tasting, gripping, testing textures, adjusting local camouflage, to the distributed intelligence of its arms and skin. This means the octopus is not a single point of perception. It is a network, a living constellation of senses. When the octopus moves through a coral head, each sucker tastes the substrate. Some detect the salty film left by grazing snails, others detect faint chemical traces left by predators. The arms reposition autonomously, forming an exploratory pattern that the central brain barely needs to monitor. Meanwhile, the skin adjusts pigment in response to shifting patches of light as the animal moves beneath a shadowed archway. The result is a creature capable of processing multiple sensory channels simultaneously without ever overloading its central system. Even hunting becomes an act of distributed intelligence. When searching for crustaceans hiding in rock crevices, the octopus explores with its arms, inserting suckers into narrow gaps. The suckers taste for prey molecules. If a crab is hiding in darkness, the arm finds it first. It may even seize the crab before the octopus's central awareness catches up. Only once the prey is captured do the signals converge, informing the central brain, which then decides how to subdue and consume the animal. This sensory autonomy explains the octopus's uncanny problem-solving abilities. It is not a creature with a single brain analyzing a single set of inputs. It is a creature whose entire body is a sensory interface interacting continuously with the environment. An octopus does not simply adapt. It collaborates with itself. But this distributed intelligence is fragile. The octopus's nervous system is designed for short lives. Intense bursts of learning, exploration, camouflage mastery, and parenting, followed by rapid decline. It is a creature built for immediacy. Its sensory world is always shifting, always responsive, always improvising. Nothing about the octopus is static, not its shape, not its color, not even the boundary between perception and action. In the reef's dim corridors, the octopus feels its world with thousands of mouths and sees its world with patches of skin. On the sandy bottom, it becomes part of the seafloor. In a kelp forest, it becomes part of the foliage. Every change in lighting, every touch, every chemical trace becomes part of its living map of reality. The octopus does not inhabit a body. It is its body, a sensory being without borders, arms that taste, skin that reads light, a brain that shares its authority with the limbs. The octopus lives inside a body made not of parts, but of perceptions, a living sensory organism constantly rewriting its relationship with the world, moment by moment. The cuttlefish drifts just above the seafloor, suspended in a column of soft, filtered light. Sand patterns ripple below, shifting as the current sweeps across the landscape. To most fish, this underwater scene appears muted, dominated by gentle blues and browns. Edges blur, reflections scatter, and the shimmer of sunlight moving across the sand holds no special meaning. But the cuttlefish sees this world through an entirely different visual channel. Its eyes widen beneath their distinctive W-shaped pupils, absorbing not just brightness and movement, but the orientation of light waves themselves. Where other animals see the ocean as a wash of color, the cuttlefish sees an overlay of hidden contrasts, a world painted in polarized patterns that reveal details invisible to nearly all other creatures. Polarized light is not a rare phenomenon underwater. Sunlight enters the ocean and becomes filtered, scattered, and stretched as it passes through waves, algae, and suspended particles. This scattering organizes light into directional bands. Most animals cannot detect these changes. Their photoreceptors register brightness and color, but not the orientation of light waves. The cuttlefish, however, possesses sensory adaptations that allow it to read these patterns easily. Its retinas contain microstructures aligned to detect polarization, granting a visual layer that operates like a separate sensory channel. It is akin to having a second set of eyes superimposed on the first, a channel that reveals the hidden geometry of light. To the cuttlefish, the glare sliding across a fish's scales is not a white flash. It is a polarized streak pointing in a specific direction. The faint outline of a shrimp moving through eelgrass becomes a shifting pattern of polarized signatures, making it stand out even when its coloration matches the blades perfectly. Even predators lurking in shadow give themselves away. Their bodies alter polarization by reflecting or absorbing light differently from their surroundings. In this world, the cuttlefish sees threats and opportunities long before shape or color becomes apparent. This ability is enhanced by one of the most unusual pupils in the animal kingdom. The cuttlefish's W-shaped pupil is not an aesthetic oddity. It is a functional tool for complex light management. Above water, pupils adjust size to control brightness. Underwater, brightness is only one part of the visual challenge. Here, light refracts unpredictably, contrast shifts dramatically with angle, and depth perception becomes distorted. The W-shaped pupil mitigates these effects by breaking incoming light into zones. Each curve of the W modulates a different direction of light, allowing the cuttlefish to maintain balanced contrast across a wide field of view. This helps prevent washout in bright zones and dark loss in shadowed areas, creating a more stable visual field. In addition to this specialized pupil, cuttlefish possess an unusual focusing mechanism. Where most vertebrates adjust the shape of the lens to change focus, cuttlefish move the entire lens backward and forward, like a camera on a track. This allows them to refocus instantly as they shift from observing distant silhouettes to examining fine details on the substrate. Their ability to adjust sight rapidly grants them exceptional precision during hunts. A shrimp trying to hide among sand grains still generates a faint polarized halo, and the cuttlefish's focusing mechanism sharpens that signature with remarkable immediacy. These visual adaptations give the cuttlefish an extraordinary understanding of its surroundings. But the sensory brilliance of the species extends beyond perception into expression. While many animals see the world in color or brightness alone, cuttlefish communicate through patterns of light and polarization on their own bodies. Chromatophores, pigment-containing cells, expand and contract under direct neural control, forming dynamic displays that move across the skin like animated textures. Beneath these chromatophores, iridophores reflect light in specific ways, often creating polarized signals invisible to predators, but visible to other cuttlefish. This dual-layer skin system acts as a living screen. The upper layer handles pattern and brightness for camouflage. The deeper layer handles polarized reflection for communication. The result is a brilliant evolutionary compromise. Cuttlefish can remain completely hidden from predators while simultaneously projecting signals to their own species. A predator might see only a patch of mottled sand. Another cuttlefish sees a shifting ripple of polarized stripes indicating threat, courtship, submission, or curiosity. The complexity of these patterns is astonishing. A cuttlefish can display high-contrast strobing bands along one side of its body, visible to other cuttlefish, but blended into the environment from a predator's view. The opposite side of its body may remain locked in camouflage, matching the texture and color of the seafloor precisely. Few animals can communicate directionally, sending a message to one observer while remaining invisible to others. The cuttlefish achieves this through the interplay of chromatophores and polarization-sensitive iridophores, updated constantly by one of the most sophisticated nervous systems in invertebrates. This means that the cuttlefish not only sees a hidden world, it actively participates in it. The animal's skin is an extension of its visual language. When two cuttlefish face each other, their polarized patterns create a conversation of flashes, ripples, and gradients that pass entirely unnoticed by predatory fish. These signals reveal intent. A male cuttlefish may flash a polarized stripe to warn a rival while simultaneously using color-matching camouflage to avoid detection by a passing grouper. During courtship, males produce sweeping waves of polarized light along their flanks, forming patterns that are seductive to females but nearly invisible to other species. This communication is not limited to mating and social encounters. Cuttlefish also use skin patterns to manipulate prey. In certain hunting situations, a cuttlefish approaches a shrimp or small fish with a slow, mesmerizing ripple of stripes along its arms. These motion patterns, visible in polarized contrast, can confuse or hypnotize prey just long enough for the cuttlefish to strike. The prey sees movement but struggles to interpret its meaning, hesitating at the critical moment. Meanwhile, the cuttlefish calculates distance, angle, and timing with millisecond accuracy, its lens shifting position as it prepares for the strike. In the dim underwater world, where shapes blur and colors fade, the cuttlefish's polarized vision offers a clarity no other fish can match. It distinguishes transparent prey, detects reflections bouncing off the sea floor, and identifies predators that believe themselves well hidden. When the cuttlefish glides across a coral ledge, its W-shaped pupils maintain stable contrast, while its polarized sensitivity reveals changes in the water's optical structure. The environment becomes a multi-dimensional tapestry of shadow, brightness, and polarized orientation, a kind of vision that blends photography, radar, and light field mapping into a single sensory experience. This sensory richness requires extraordinary neural control. The cuttlefish's brain is among the largest of any invertebrate relative to body size, with specialized lobes dedicated to vision, movement, and skin pattern regulation. Its nervous system processes contrast at speeds that allow instantaneous camouflage adjustments. Within fractions of a second, the cuttlefish can shift from bright, bold stripes used for signaling to muted, complex camouflage capable of matching sand, rock, coral, or algae. These adjustments often occur faster than the observer can detect. The skin does not merely respond to commands, it negotiates with the eyes, adapting to local lighting measured through both external vision and internal skin-based photoreception. This is the essence of the cuttlefish, a creature that sees with extraordinary sensitivity and expresses itself through a body that is both canvas and instrument. No other marine animal combines visual acuity, polarized detection, directional communication, and instant camouflage with such precision. The cuttlefish navigates a visual universe layered far beyond human comprehension, a world of hidden contrasts, shimmering silhouettes, polarized halos, and signals broadcast in wavelengths most animals never perceive. Within this special sensory realm, the cuttlefish thrives. It hunts by reading invisible clues. It hides by blending into complexity. It communicates by painting its skin with messages that only certain eyes can interpret. It perceives the ocean through a richer palette of light than nearly any other creature. In its luminous, shifting world, the cuttlefish is both observer and signal, predator and display, a living screen illuminated from within, a communicator in a visual language others cannot see, a master of polarized perception and chromatophore artistry. The cuttlefish does not merely survive in this hidden world of light, it creates it. The tide recedes, revealing a landscape of slick rocks, scattered shells, and drifting strands of algae. Tiny rivulets run between the stones, carrying fragments of the ocean back toward deeper water. In this shifting intertidal world, where light bends across ripples and shadows dance unpredictably, the crab emerges as one of the most perceptive creatures on the shore. It scuttles sideways across the rocks, its movements quick and precise, each step carefully calculated. But despite its alert posture and restless legs, the crab is not relying primarily on sight. Instead, it perceives its world through a layered sensory system that blends vision, taste, and touch into a single integrated stream of information. To a crab, the world is composed of moving shadows and chemical traces, signals that reveal danger, opportunity, and the presence of life long before anything ever comes into view. At first glance, the crab's eyes seem small compared to its armored carapace. But these compound eyes, perched on long stalks, are extraordinary sensory structures. Each eye contains thousands of tiny facets, called ommatidia, arranged in a mosaic that captures the environment from nearly every direction. Unlike vertebrate eyes, which create detailed images from focused light, compound eyes excel at detecting motion. Even the slightest disturbance, a shadow passing overhead, a fish darting between tidal pools, a bird swooping low, produces an immediate visual cue. The crab does not need high resolution. It needs awareness. And with its eye stalks capable of swiveling independently, it maintains a panoramic field of view few animals can match. A crab can observe the world around it while still focusing on its immediate task. It sees danger approach from behind, from above, or from the edges of its peripheral field long before most predators realize they have been detected. But vision is only one part of the crab's sensory world. While its eyes detect movement and shadows, its antennae interpret the chemical story of the environment. Every wave that washes over a tide pool, every splash of surf, carries with it a constellation of molecules released by plants, animals, and decaying matter. These molecules bind to specialized chemoreceptors located on the crab's antennae and mouthparts. With every flick of its antennae, the crab samples the water, reading it like a shifting chemical script. A hint of amino acids drifting from a buried clam reveals the potential for food. A trace of pheromones left by another crab signals the presence of a mate or a rival. The faint chemical residue of a fish passing moments earlier leaves a directional trail that the crab can follow or avoid. Crabs rely so heavily on chemical detection that, even in complete darkness, they can navigate toward food sources just by brushing their antennae across the water surface. These antennae are in constant motion, sweeping, tapping, and sampling. The crab's legs also contain chemoreceptors, giving its limbs the ability to taste the substrate the same way its antennae taste the water. When a crab walks across sand, it is not merely stepping, it is interpreting. Certain sediments carry the scent of buried prey. Others contain the chemical signatures of competitors or predators. The crab's legs, antennae, and mouthparts collect these inputs and funnel them toward its nervous system, which integrates the information into a sensory map more detailed than any produced by vision alone. This reliance on dual sensory modes, all-around vision and chemical detection, shapes every aspect of a crab's life. When searching for food, the crab often follows chemical trails left by decaying matter or microorganisms thriving beneath algae mats. As it approaches a potential food source, its antennae intensify their sampling, sweeping back and forth with increasing frequency. It is as if the crab tastes the water ahead of it before committing to the next step. If the chemical signals strengthen, the crab digs or probes the substrate with its legs. If the signals weaken, it changes direction. A navigational strategy that allows it to locate food even when visibility is reduced by churning waves or silt. In turbid water, most animals lose their advantage. But crabs thrive in this environment precisely because the lack of visual detail does not hinder their primary senses. Vision gives them motion cues, the broad strokes. Chemical detection gives them detail, the fine print. Combined, these systems create a sensory world that is both wide and intimate, both immediate and directional. When danger approaches, the crab relies on its eye stalks first. A sudden flicker of movement, a shifting shadow, or the pattern of light broken by a predator overhead sends instant signals to the nervous system. The eyes do not need high-detail silhouettes. A looming blur is enough to trigger a defensive response. But chemical signals reinforce these visual warnings. The scent of a fish lingering in the water reveals not only recent presence, but also relative freshness. If the chemical trail is strong, the predator is near. If it is faint, the crab may continue feeding. Crabs also use chemical cues for social interactions. Males follow trails left by receptive females. Females detect the presence of larger, dominant males through subtle pheromones. Competitors leave signatures in the sand, and crabs interpret these signals to avoid unnecessary conflict. In this way, chemical communication organizes entire crab communities without requiring direct visual contact. Even territorial boundaries are maintained through these molecular messages. The crab's compound eyes provide additional advantages in the complex, cluttered environment of rocks and tide pools. By elevating the eyes on stalks, the crab can hide most of its body beneath a rock while still scanning the area for predators or rivals. It can peer over barriers without revealing its position. This ability is crucial in ecosystems where predators strike from above, such as birds or fish hunting in shallow water. The crab's eyes can withdraw instantly into protective sockets when threatened, preserving the delicate sensory structures. But the crab's sensory integration does not end with sight and chemical detection. Mechanoreceptors on its legs detect vibrations traveling through the substrate, waves slapping a rock, footsteps of a predator, or the burrowing movement of prey. All send mechanical signals that crabs interpret quickly. In many cases, a crab will respond to substrate vibrations even before visual or chemical cues arrive, allowing it to escape or prepare for defense with impressive speed. To a crab, the environment is alive with signals. A grain of sand is not just a grain of sand. It is a carrier of microscopic molecules that tell stories of recent events. A change in water flow is not only physical movement, it is the arrival of new chemical cues. A shadow passing overhead is a warning, but the real confirmation comes from the molecules drifting behind it. The crab constantly cross-references these sensory channels. If a shadow appears without accompanying chemical cues, it might be harmless, seaweed swaying in the current. But if both shadow and chemical trace align, the crab reacts instantly. This layered sensory world extends beyond survival. It shapes the crab's role in the ecosystem. As crabs patrol rocks and sand, they stir sediments and redistribute nutrient-rich materials. Their movement patterns, guided by chemical gradients and visual cues, help aerate the seafloor and cycle organic matter. Even their territorial behaviors contribute to the landscape by influencing where algae grow and where scavengers congregate. In this way, crabs are not merely inhabitants of the intertidal zone. They are active shapers of it, guided by sensory perception that goes far beyond the limits of human experience. The tide rises, waves increasing their reach across the rocks. Water fills tide pools again, and the sensory world of the crab becomes richer. Chemical trails swell with new inputs. Visual cues shift as reflections grow sharper. The crab adjusts its posture, antennae sweeping continuously, eyes rotating to maintain awareness. It does not experience the world as a static environment, but as a fluid tapestry of signals, some fleeting, some lasting, all meaningful. In this dynamic coastal zone, the crab thrives because it does not rely on one sense alone. Its vision captures motion from nearly every direction. Its antennae and legs taste the water and substrate with exquisite sensitivity. Its mechanoreceptors interpret vibrations. Together, these systems create a sensory world that few animals can rival. Where humans would see a blur of reflections and waves, the crab sees warnings, opportunities, and hidden trails. Where humans would smell nothing, the crab detects a chemical script that reveals the unseen. Its world is both broad and detailed, illuminated by shadows and written in tastes. To a crab, reality is a layered mosaic, shadows shifting above, molecules drifting below, all of it merging into a complete picture that guides every step across the rocks and sand. The seafloor at night is a world without outlines. The water absorbs what little light remains, leaving the landscape flattened into gradients of darkness and shifting faint glimmers where bioluminescent organisms, pulse or sediment catches a stray photon. For most animals, night on the benthic plain is a time to hide, to wait until dawn brings clarity. But for the lobster, this is the moment when the world becomes readable. The darkness that blinds others reveals its complexity to the lobster through scents, microcurrents, and even the faint imprint of the planet's magnetic field. While other creatures navigate by sight or sound, the lobster moves through an invisible architecture, a network of chemical pathways, tactile vibrations, and magnetic cues that turn the seafloor into a landscape rich with information. A lobster emerges from its shelter, a crevice carved into rock by tides and time. Its antennae sweep outward like two deliberate probes. Each movement covers broad arcs of water, filtering particles, testing chemical gradients, registering the faintest hints of organic decay or injured prey. Lobster antennae are not passive. They are lined with microscopic sensory hairs, each containing chemoreceptors tuned to complex mixtures of amino acids, peptides, and organic molecules. These receptors read the water the way a skilled tracker reads footprints in soil. Every passing current carries fragments of distant events: a fish struggling after an injury, a snail crushed by a predator, a piece of carrion drifting against the bottom. These chemical signals diffuse through the darkness, forming plumes that stretch across the seafloor like invisible rivers. The lobster's legs also participate in this sensory world. As it walks, each step presses sensory hairs against the substrate, picking up chemical residues that adhere to sand grains, algae, or the shells of other creatures. Lobsters smell not only through the water, but through direct contact with the ground. Their legs become taste buds capable of interpreting where food has been, where competitors have moved, and where predators have passed. A trail that is invisible to the eye becomes a chemical signature beneath the lobster's feet, a script written in molecules. Darkness does not impede the lobster. It enhances its sensory reach. During daylight, chemical trails disperse among turbulent currents created by surface waves. At night, the ocean calms. Tidal movements continue, but the water becomes more stratified, allowing chemical plumes to stretch farther and maintain their structure. A lobster navigating the seafloor can detect these gradients from astonishing distances. Its antennae flick repeatedly, each stroke sampling a slightly different portion of the water column. The lobster follows these gradients the way a person might follow the smell of smoke to find fire, except its sensitivity is far beyond human perception. A faint thread of decaying flesh in the water gives the lobster direction. A shift in gradient intensity tells it whether it moves toward or away from the source. This chemical navigation makes the seafloor, otherwise flat, dark, and devoid of obvious landmarks, feel like a richly textured map. Where humans would see only obscurity, the lobster perceives highways of smell sweeping across the bottom. Every plume has shape. Some narrow and concentrated, others wide and diffuse. The lobster interprets these invisible structures with confidence. Its antennae do not simply detect presence, they decode directionality. Molecules arriving from the right side indicate a source upstream. Faster arrival rates signal proximity. Mixed chemical signatures reveal layered stories: a dying fish near a decomposing plant patch, or multiple prey animals feeding near a rocky outcrop. But chemical cues alone do not anchor the lobster's movements. The seafloor, for all its complexity, remains vast. Chemical plumes shift with tides and currents, sometimes dispersing entirely after a storm or strong current. Lobsters need a broader navigational tool, a cue that remains stable when their chemical map dissolves. Research suggests that many lobsters possess exactly that, an internal magnetic compass. Experiments conducted on certain lobster species indicate that they detect Earth's magnetic field and use it as a crude but dependable navigational grid. They respond not only to compass direction, but to magnetic inclination and intensity, which vary across geography. These magnetic gradients provide a kind of underwater map. When a lobster sets out from shelter to forage, often traveling considerable distances, it relies on chemical cues to find food. But when it must return home, whether to a favored crevice, a sandy burrow, or a protected outcrop, it switches sensory modes. Chemical cues at this point become less reliable. They do not lead home. Instead, the lobster taps into magnetic orientation, aligning its movement with patterns imprinted in its nervous system. Through this system, it can return to the same shelter night after night, even when currents have erased every chemical cue. The magnetic map is not precise in the way a human map is, but it is consistent. It ensures the lobster never becomes lost in the vast, dark expanse of the bottom. This combination, chemoreception and magnetoreception, creates a sensory world unlike that of most marine animals. The lobster experiences the ocean as a layered environment. At one level, it follows chemical trails produced by life and death. At another level, it uses Earth's magnetic field to maintain directionality. Overlapping these systems are mechanosensory cues on its legs and antennae. Tiny vibrations, shifts in sediment underfoot, and pressure changes all feed into its sensory stream. As the lobster walks across rock or sand, its long antennae remain in constant motion, sweeping forward and outward. Every few steps it shifts its posture, lifting slightly to sample a new layer of water. The chemical plumes do not reveal themselves immediately. They intensify gradually, becoming thicker and more defined as the lobster nears their origin. When the plume widens, the lobster adjusts course. When it narrows, it zeroes in. As it approaches the source, a piece of carrion wedged between rocks perhaps, its antennae vibrate with chemical intensity. Its claws extend outward, testing texture, while its legs taste the substrate's molecular residue. Even in absolute darkness, the lobster knows precisely where to go. Predators too generate chemical signatures. A fish that has recently hunted carries the molecular imprint of its prey. A wounded predator leaks subtle cues into the water. The lobster interprets these signals as cautions. A sudden decrease in chemical diversity in a patch of water might indicate that the predator recently passed through, leaving behind a silent void. Lobsters avoid these areas instinctively, their legs and antennae guiding them away before their eyes perceive anything. Because crabs, fish, and eels share similar habitats, the lobster's sensory toolkit doubles as a survival mechanism. The magnetic orientation ensures that even in panic when fleeing from danger, the lobster's escape trajectory is not random. The animal can flee quickly, then correct course using geomagnetic cues, eventually circling back to familiar shelter. This consistency, born of a biological sensitivity to forces invisible to many animals, gives the lobster a remarkable ability to maintain territorial boundaries and feeding routes over long periods. As the night deepens, the lobster moves steadily across the seafloor. It encounters rocks slick with algae, patches of coarse sand, the remains of kelp torn apart by storms, and the shells of mollusks scattered across channels. The lobster tastes these environments through contact receptors on its legs, learning where the prey has been active and where competitors have fed. Each step provides data. Each antenna flick provides direction. Nothing about this journey appears complex from a distance. To human eyes, it looks like a slow, steady crawl across darkness. But internally, the lobster is mapping constantly. Chemical gradients stretch before it. Magnetic inclination provides orientation. Tactile feedback reveals substrate stability and the presence of shelters. The sensory world beneath the ocean surface is richer, more layered, and more dynamic than anyone standing on a boat deck above could ever imagine. The lobster eventually reaches an area where chemical signals intensify abruptly. The water tastes of decomposing flesh. The plume tightens into a concentrated band. The lobster follows it, stepping sideways with increasing confidence. Soon it finds its target, a piece of dead fish caught between rocks. Using its claws, it tears off chunks and feeds, its antennae still sweeping the water for predators. When the lobster finishes, it turns back toward home. The chemical trail is now useless. The prey is consumed. The seafloor offers no visual markers. It is a void of darkness once again. And yet the lobster does not wander. It straightens its body, aligns with the Earth's magnetic field, and begins a steady return toward the shelter it left earlier in the night. The magnetic map guides it. Its chemical senses monitor the environment, and the seafloor becomes once again a network of invisible highways and signposts that only the lobster can read. The lobster's world is sensory architecture, complex, layered, invisible, and alive. Chemical plumes guide it outward. Magnetic cues bring it home. Together they turn darkness into navigation. The lionfish drifts across the reef with a slow, hypnotic grace. Its body barely moves, yet its long fin rays trail outward like delicate banners, flickering slightly in the water. To the casual observer, these fins appear ornamental, as though nature had added extravagance for spectacle alone. But beneath this display lies one of the most sensitive sensory systems in the reef. The lionfish is not merely drifting, it is scanning, reading the water with a radar-like precision that allows it to approach prey so silently and so closely that escape becomes impossible. In the dim maze of coral pillars and hollow caves, the lionfish transforms the subtle flow of water into a sensory map, a private world of vibrations and microcurrents that most reef fish cannot even perceive. A small fish moves ahead, too focused on feeding to notice the danger creeping behind it. The lionfish advances with almost impossible slowness. Its pectoral fins expand and contract subtly, shaping its trajectory while disturbing the water so little that even sensitive prey species fail to detect the approach. Every extended fin ray responds to water displacement. Slight differences in flow direction slide across the lionfish's fins, bending the rays gently and activating mechanoreceptors embedded along their length. These receptors inform the lionfish of the prey's distance, orientation, tail beats, and moment-to-moment adjustments. Each fin acts as a separate sensor. Together, they create a three-dimensional field of detection, a sensory bubble the lionfish uses to surround its prey. This sensory bubble is not fixed. It flexes and shifts with the lionfish's movements. As the predator glides forward, the fin rays interpret pressure waves generated by the small fish's breathing, subtle wiggling or twitching fins. The predator does not need vision to track the target. Even with its eyes closed, it could follow the prey by reading vibrations alone. Yet vision still plays a crucial role. Lionfish eyes are large, forward-facing, and adapted to detect motion within complex coral habitats. Their pupils expand widely in dim environments, maximizing sensitivity to shadow shifts created by prey weaving among coral branches. The lionfish's eyes, combined with its fin sensors, create a dual input system that surpasses the capabilities of most reef predators. Where many hunters rely on short bursts of speed to overpower prey, the lionfish relies on accuracy earned from sensory integration. As the lionfish approaches, its lateral line system activates. Running along the length of the body, the lateral line detects pressure changes and vibrations in the water. It is essentially a biological flow sensor. In the lionfish, this system is exceptionally refined, complementing the fin ray sensors. Together they detect approaching currents, sudden changes in turbulence, and the faint pressure waves produced by fleeing prey. These combined signals allow the lionfish to position itself at the perfect strike distance, close enough to attack successfully, but far enough not to trigger a startle response. The small fish ahead feels no alarm. Its lateral line, less refined than the lionfish's, does not register the predator's approach. Lionfish movement is so slow, so controlled, that it falls below the threshold for detection. Many prey fish flee only when a predator creates a rapid pressure wave or turbulence spike. The lionfish avoids this entirely. It advances at a speed too low to produce a meaningful pressure signature. This is the essence of its hunting strategy. Not stealth through hiding, but stealth through hydrodynamic invisibility. Now within striking distance, the lionfish begins a second phase of sensory control. Its pectoral fins flare outward, expanding into wide, feather-like panels. These fins are not merely used for propulsion, they are tools of manipulation. By expanding them, the lionfish creates a visual barrier that channels the prey into a confined space. But it is more than visual control. The flared fins also alter the flow of water, creating microcurrents that discourage escape in certain directions. The prey, feeling subtle pressure changes, interprets them as obstacles, turning instinctively away from the open fin surfaces. The lionfish uses this behavior to corner the prey against coral or against the predator's own body. Throughout this process, sensory feedback remains constant. The fin rays continue to read pressure changes. The lateral line monitors vortices created by the prey's attempts to escape. The lionfish adjusts its fins in response, creating a dynamic cage of water and motion. To the small fish, the space seems to shrink around it. Every attempt at escape leads into another barrier, another flow pattern that subtly redirects its path. The lionfish's control is not physical, but sensory, manipulating the prey's reactions through invisible forces. The lionfish's eyes lock onto the final position, calculating the distance needed for its rapid forward suction strike. When the moment arrives, it acts with explosive precision. The lionfish opens its jaws, expands the cavity of its mouth, and generates a suction force that pulls the prey in before it can react. The strike lasts only a fraction of a second. The prey disappears in a pulse of motion. The fins relax. The lionfish's radar bubble collapses momentarily before the predator resumes its slow drift across the reef. This hunting style gives the lionfish an unfair advantage in reef ecosystems where prey species evolve to detect fast-moving predators like groupers, jacks, and barracudas. Few native reef fish are adapted to a predator that hunts through stillness. The lionfish brings a sensory sophistication uncommon among fish its size, a blend of mechanosensory precision, hydrodynamic control, and visual awareness that results in near-perfect ambush success. At night, this sensory ability becomes even more valuable. Darkness erases visual cues. Coral branches sway unpredictably. Prey fish sleep tucked into crevices, gills pulsing slowly. Night currents soften, and disturbance signals travel farther. The lionfish uses its fin sensors and lateral line to navigate this quiet world. A sleeping fish exudes gentle micro-vibrations from its opercular movements. The lionfish can detect these pulses from surprising distances, homing in until it hovers just centimeters away, suspended in perfect stillness. Its fins expand again, forming a sensory cage even in darkness. The prey's escape routes disappear. The lionfish's radar-like sensing extends beyond hunting. As it moves across the reef, the fin rays detect the presence of obstacles before the eyes see them. This allows the lionfish to maneuver through tight coral structures without touching sharp surfaces that could damage its soft fins or venomous spines. The lateral line also helps detect incoming threats, such as large predators passing nearby. Even when lionfish do not visually register an approaching grouper, the pressure wave produced by the grouper's movement triggers immediate evasive reactions. In ecosystems where lionfish are invasive, their sensory prowess contributes to their ecological dominance. Native prey fish, unfamiliar with this style of approach, fail to interpret lionfish movements as predatory. By the time they detect the danger, they are already within the sensory cage. In areas like the Western Atlantic, where lionfish have expanded rapidly, prey populations decline not only because of high consumption rates, but because the prey's sensory systems are mismatched against the lionfish's unique hunting strategy. Yet even in their native Indo-Pacific habitats, lionfish maintain this sensory mastery. Their slow, floating movement allows them to blend visually with drifting algae or sea fans. Their striking patterns disrupt their outline, and their silent hydrodynamic presence ensures that prey does not recognize them as hunters until it is far too late. When the lionfish settles onto a reef ledge, it appears motionless. But internally, its sensory systems remain active. The lateral line reads water flow. The fin rays interpret pressure gradients. The eyes scan for movement. All these inputs merge into a single sensory experience, a world constructed from touch, vibration, and shadow, more than sight alone. The lionfish occupies a sensory bubble that moves with it, a constantly updating map of the reef's inhabitants and invisible currents. To the lionfish, the reef is not chaotic. It is structured, full of gradients and signals that define opportunity. The fin rays trace motion. The lateral line reads pressure. The eyes track shadows. Together, they create a sphere of control, a radar field that allows the lionfish to close in on prey without sound, without warning, without escape. The lionfish does not chase. It surrounds. It does not startle. It suffocates options. In the silent world of the reef, its fins become sensors, barriers, and weapons, turning stillness into the deadliest hunting strategy of all. The sea urchin sits motionless on the seafloor, a dark sphere of spines rising from the sand like a living piece of geology. At first glance, it appears simple. A creature without a face, without limbs, without any obvious sensory organs. Waves pass overhead, and light ripples across its spines. But nothing external reveals how this slow, armored animal perceives the world. Yet beneath that rugged exterior lies one of the strangest sensory systems in the ocean. Unlike fish, cephalopods, or crustaceans, the sea urchin has no eyes. Instead, its entire body is an eye, a living, distributed photoreceptive machine that interprets light, shadow, and direction through thousands of microscopic sensors scattered across its surface. Where other animals focus vision through a set of lenses, the sea urchin assembles a crude but functional image from the sum of its body. This strange form of vision begins with photoreceptor cells embedded throughout the animal's skin. These cells are not organized into a retina or arranged into a structured eye. They are distributed among the spines, between the plates of the test, and across the soft tissue surrounding the tube feet. Each individual receptor detects brightness and directionality. Alone, each cell provides almost no information. But together, across hundreds or thousands of points, they generate a directional picture of the environment. The urchin does not see sharp edges, or color, or fine detail. It detects gradients, where the light brightens, where shadows deepen, where predators or open water create large moving silhouettes above. For the urchin, this minimal sight is enough. In a world where exposure means danger and shelter means safety, it does not need to recognize predators by shape. It needs only to detect looming darkness or sudden brightness to trigger movement. Light is its map. Shadow is its warning. As the sun shifts across the water, the urchin's spines cast their own shadows onto its body. These shadows, in turn, change the incoming light that the photoreceptors detect. The animal interprets these differences, using spine orientation as part of its sensory toolkit. Some species even use their spines like crude eyelids, angling them to block or concentrate light. In this way, the urchin transforms its armored exterior into a dynamic optical structure. Not a focused lens, but a field of shading devices that refine the flow of light reaching the photoreceptors below. The result is astonishing. The sea urchin effectively turns its entire spherical body into a low-resolution compound eye. When a shadow passes overhead, perhaps the silhouette of a fish or an octopus, the photoreceptors on the upper surfaces detect the shift long before the urchin's tube feet sense the movement. The urchin reacts by lowering its spines or curling slightly inward, using its entire body as a shield. If the shadow persists or grows, the urchin begins to move, using rows of tube feet on its underside to migrate toward darker, safer ground. These movements do not appear coordinated by detailed imagery, but by relative direction. If one side of the body receives less light, the urchin interprets that as refuge and drifts toward the darker region. Movement in sea urchins is not rapid, it is deliberate. Each tube foot acts as a small suction device, extending and retracting through water pressure controlled inside the animal's water vascular system. These tube feet attach to rock, sand, or algae, forming a slow but steady crawling motion. As they move, additional sensory systems engage. Tube feet are covered in chemical receptors, allowing the urchin to taste the substrate as it searches for food or shelter. They also contain touch receptors, detecting surface texture, cracks, or the presence of predators or competitors. Combined with the body's diffuse vision, these tube feet add essential detail, surface safety, direction of obstacles, and chemical signals that reveal food sources or danger. To the urchin, the world is constructed from layers of sensory input: brightness, shadow, pressure, texture, and taste. It has no central image, no internal projection of shapes. Instead, it acts on gradients: a rising slope of light in one direction, a falling shadow in another. For a creature with no head, no face, no specialized organs, this system is elegant. It is vision reduced to its bare essentials, yet it is effective enough for the urchin to survive in habitats ranging from shallow tide pools to deep reefs where light barely reaches. Even the structure of the sea urchin's skeleton contributes to its visual abilities. The test, the hard shell, is made of porous calcium carbonate plates that diffuse and scatter light. This scattering helps smooth out the visual field, reducing the noise that any one photoreceptor might detect. The spherical shape provides an omnidirectional canvas for light detection. Where most animals build eyes to project a unified field of view, the sea urchin uses geometry itself as part of its sensory architecture. As the urchin moves across the sea floor, it constantly updates its orientation in response to shifting light. If a bright patch appears suddenly, perhaps from a predator disturbing sediment or the sun breaking through waves, the urchin moves away. If darkness settles over part of its body, the urchin moves toward it, seeking the protective cracks and crevices that define its safe zones. Predators struggle to anticipate this behavior. A fish approaching from above might expect the urchin to remain still. After all, it has no eyes to see the threat. Yet the urchin senses the fish's shadow in advance and lowers its spines in a defensive halo. For species with venomous spines, this reaction is enough to discourage many attackers. Even in less armored species, spine adjustment can deter predators by making the urchin harder to swallow or manipulate. More remarkably, some species appear able to orient themselves toward food using gradients of light as indirect cues. Decaying algae or microbial mats often grow in shadowed crevices, while barren sand reflects more light. The urchin uses minimal vision to avoid bright, open areas where food is scarce, then switches to touch and chemical sensing once it reaches darker patches. Its tube feet sweep across the substrate, tasting for dissolved organic matter and feeling for the textures of algae-covered rock. This layered sensory world allows the sea urchin to build a crude environmental picture, even though no part of its body sees in the traditional sense. The urchin does not assemble images. It navigates based on the direction of safety or danger encoded by brightness gradients. Its senses function more like those of a plant responding to sunlight than those of a typical animal. Yet the urchin is not passive. It reacts actively, pulling away from threatening light, raising or lowering spines for defense, or pushing toward shaded feeding grounds with gradual but determined motion. In deeper waters, where light is scarce and colors fade to blues and grays, the urchin's distributed photoreceptors become even more crucial. Here, subtle changes in light can signal predators approaching from a distance. Even small shifts create silhouettes that the urchin interprets as danger. Because its body detects light from all directions, it has no blind spots. Its vision, although crude, wraps around its entire form. This form of whole-body perception hints at a much older evolutionary strategy, one that predates the complex eyes of vertebrates and cephalopods. Instead of concentrating vision into a pair of organs, the sea urchin spreads it across its entire surface. It is an organism in which the border between body and sensory organ disappears. Every spine, every patch of skin, every tube foot contributes to perception. In a world where precision is unnecessary, the sea urchin thrives by reading the simplest signals. Light means danger. Darkness means shelter. Texture means opportunity. Chemical traces mean food. From these primitive ingredients arises a functional map of the world. The sea urchin does not see in images. It sees in gradients. It sees in shadows. It sees in safety. Its entire body becomes a single, low-resolution eye, one that never blinks, never looks away, never stops, reading the faint patterns of light slipping through the sea.